On the 2nd of June 2011, astronomers operating the Optical Gravitational Lensing Experiment telescope at Las Campanas Observatory in Chile detected something impossible to see directly. The OGLE survey, designed to catch brief brightenings of distant stars, recorded an event designated OGLE 2011b LG 0462. At the same time, 6,500 miles away in New Zealand, the Microlensing Observations in Astrophysics collaboration spotted the identical event through their 1.8-meter telescope at Mount John Observatory, cataloguing it as MOA 2011b LG 191. Two independent teams, two telescopes on opposite sides of the planet, both watching the same impossible thing happen. The event lasted 270 days. A background star in the galactic bulge, the dense central region of the Milky Way, roughly 27,000 light-years from Earth, suddenly brightened by a factor of several hundred, held that brightness for months, then gradually faded back to normal. This wasn't a supernova. The light curve showed a specific symmetrical shape that astronomers recognize instantly: gravitational microlensing. Something massive had passed directly between Earth and that distant star, bending space-time enough to magnify the star's light like a cosmic magnifying glass. But there was nothing visible doing the magnifying. No star appeared at the lensing position, no galaxy, no glowing accretion disk, just empty space, or what appeared to be empty space. The lensing object was completely dark, emitting no light whatsoever across the electromagnetic spectrum. Follow-up observations with the Hubble Space Telescope in 2011 and again in 2017 confirmed the absence of any luminous companion. Whatever bent space-time had no light source of its own. Kailash Sahu, an astronomer at the Space Telescope Science Institute in Baltimore, led the analysis team that spent years studying this event. Using Hubble's exquisite resolution, capable of measuring positions to 1/10 of a milliarc-second, Sahu's team tracked not just the brightening, but the apparent displacement of the background star's position. As the massive dark object passed in front, it didn't just magnify the star's light. It actually shifted the star's apparent position on the sky by 2.82 milliarc-seconds, an angle so tiny it's equivalent to measuring the width of a human hair from 1,000 miles away. This displacement measurement was crucial. The duration of the lensing event, the degree of magnification, and the size of the positional shift together allowed the team to calculate three fundamental properties of the invisible lens: its mass, its distance from Earth, and its velocity through space. The numbers that emerged told a story of something extraordinary. The mass came out to 7.1 times the mass of our Sun, with an uncertainty range between 6 and 8.4 solar masses. The distance, 5,150 light-years from Earth, placing the object roughly halfway between us and the galactic center, embedded within the Milky Way's disk. The velocity, 45 kilometers per second, relative to the average motion of stars in that region of the galaxy. This speed, while fast by everyday standards, about 100,000 miles per hour, is actually slow for an ejected object, suggesting a relatively gentle departure from wherever this object originated. But the mass was the smoking gun. There are only two types of compact objects that can have masses in this range: neutron stars and black holes. Neutron stars, the collapsed cores of massive stars supported by neutron degeneracy pressure, have a theoretical maximum mass around 2.5 solar masses, though the exact limit depends on the equation of state for ultra-dense nuclear matter. Some exotic models push this limit as high as 3 solar masses. But 7 solar masses? That's impossible for a neutron star. The object had to be a black hole. This wasn't just any black hole. Stellar mass black holes, those formed from the collapse of massive stars, usually reside in one of two situations. Either they're in binary systems with a companion star stealing matter from that companion and glowing brilliantly in X-rays as the stolen material spirals inward through an accretion disk heated to millions of degrees. Or they're inside dense star clusters where gravitational interactions occasionally fling them into encounters with stars. But this black hole was doing neither. It was alone, drifting through the galactic disk with no companion star, no accretion disk, no galaxy, no cluster. Just a solitary 7 solar mass gravitational trap, invisible except for the subtle warping of space-time that briefly magnified a background star. The discovery raised immediate questions. How does a black hole end up alone? Stellar mass black holes form inside massive stars when those stars exhaust their nuclear fuel and collapse. These progenitor stars typically have masses of at least 20 to 25 times the Sun's mass. When such a star goes supernova, the explosion should either leave the black hole in roughly the same location, perhaps with a small kick from asymmetric explosion dynamics, or launch it away at high velocity if the explosion is particularly asymmetric. But this black hole's relatively modest velocity suggested something more complex. Moreover, stars that massive don't form in isolation. They're born in giant molecular clouds alongside hundreds or thousands of siblings, and these stellar nurseries eventually disperse into open clusters or stellar associations. If a 2-5 solar mass star formed in such a cluster underwent supernova and left behind a black hole, that black hole should still be in or near the cluster, yet no cluster is visible at the black hole's location. Either the cluster dispersed completely in the time since formation, or the black hole was ejected from its birthplace and has been wandering for millions of years, or something else entirely happened. The 2022 paper announcing these findings, published in the Astrophysical Journal, marked a milestone, the first definitive detection of an isolated stellar mass black hole through astrometric microlensing. Previous candidates existed other lensing events with similar characteristics, but none had the combination of long-duration observation, high-precision Hubble measurements, and clear mass determination that ruled out alternatives. OGLE 2011b, LG 0462/M, OA 2011b, LG 191 was the gold standard, the unambiguous case that proved such objects exist, black holes wandering the galaxy alone, invisible except when they happen to pass in front of distant stars and reveal themselves through Einstein's predicted bending of light, the gravitational lens that bent starlight across 5,000 light-years. Albert Einstein published the general theory of relativity in November 1915, replacing Newton's picture of gravity as a force with the radical idea that mass curves space-time. Heavy objects create dips in the fabric of space and time, and other objects move along the curved paths geodesics through this warped geometry. Light, traveling along these geodesics, bends when passing near massive objects. Einstein calculated in 1936 that if a massive object passed precisely between Earth and a distant star, the foreground object's gravity would act as a lens, magnifying the background star's light. But Einstein dismissed the phenomenon as unobservable. The alignment required was extraordinarily precise. The lensing object, the background star, and Earth had to line up to within a tiny fraction of a degree. Moreover, the magnification would be modest, perhaps a factor of 2 or 3, and would last only briefly as the objects moved relative to each other due to their different motions through the galaxy. Einstein calculated that the probability of observing such an event was vanishingly small. He wrote in his 1936 paper, published in the journal Science, that there is no great chance of observing this phenomenon. Einstein was wrong about the observability, though not about the physics. The key insight came in 1986 when Bohdan Paczynski at Princeton University proposed using gravitational microlensing to search for dark matter in the form of massive compact halo objects machos. Paczynski realized that while any individual star has a tiny probability of being lensed at any given moment, the Milky Way contains hundreds of billions of stars. If you monitor millions of stars continuously, you'll catch lensing events regularly. The technology of the late 1980 seconds was finally good enough to make this feasible. The physics of gravitational lensing comes directly from the Einstein field equations, the 10 coupled non-linear partial differential equations that relate spacetime curvature to matter and energy distribution. For the specific case of a point mass m at distance d lens from Earth, with a background source at distance d source, the mathematics simplifies considerably. The angular Einstein radius, the angular separation between the lens and the lensed image for perfect alignment, equals the square root of the quantity. 4 times Newton's gravitational constant times the lens mass, divided by the speed of light squared, multiplied by the difference between 1 over d lens and 1 over d source. When you plug in numbers for stellar mass objects at kiloparsec distances, this angle comes out to about 1 milliarc second. During a lensing event, the background star's apparent brightness follows a predictable curve. As the lens approaches alignment, the magnification increases, reaching maximum when the alignment is closest, then decreasing symmetrically as the lens moves away. The light curve has a characteristic shape, a smooth rise to peak, then a smooth decline. The duration of the event depends on the Einstein radius and the relative velocity between lens and source. For typical stellar masses and velocities, events last days to months. But there's more information encoded in the lensing than just brightening. The lens doesn't create a single magnified image of the background star, it creates 2 images, one on each side of the lens. For lensing by stellar mass objects, these images are separated by milliarc seconds, far too small to resolve with ground-based telescopes. But the Hubble Space Telescope, orbiting above Earth's atmosphere, with its 2.4-meter mirror achieving diffraction-limited resolution, can measure positions to 1/10 of a milliarc second. This precision allows astrometric microlensing, measuring not just the brightness change, but the centroid shift the change in the apparent position of the combined light from both images. The centroid shift reaches maximum when the lens is offset from perfect alignment by about the Einstein radius divided by the square root of 2. The size of this shift depends on the lens mass and distances. For the OGLE 2011BLG0462 event, the measured centroid shift was 2.82 milliarc seconds. This measurement, combined with the 270-day duration and the specific shape of the light curve, allowed Sahu's team to solve for the lens properties uniquely. The calculations involve multiple steps. First, the light curve shape determines the impact parameter, how close the lens passed to perfect alignment, and the Einstein radius crossing time, how long the lens took to move a distance equal to 1 Einstein radius. Second, the centroid shift measurement determines the angular Einstein radius directly in milliarc seconds. Third, combining these gives the lens source relative proper motion, how fast the lens moved across the sky relative to the background star. Fourth, with estimates of the distances to lens and source from their positions in the galaxy and their colors, you can calculate the lens mass. The OGLE and MOA surveys, which detected the event initially, use 1.3 meter and 1.8 meter telescopes respectively, monitoring millions of stars in the galactic bulge every clear night. When a lensing event begins, the automated detection algorithms flag it within a day or 2, allowing follow-up observations with larger telescopes. For OGLE 2011 G0462, follow-up included multiple ground-based observatories, and crucially, 8 separate epochs of Hubble Space Telescope imaging between 2011 and 2017. These Hubble observations tracked the centroid position before, during, and after the lensing event with exquisite precision. The analysis revealed something unusual about the lens. Most microlensing events are caused by ordinary stars, red dwarfs, white dwarfs, or main sequence stars of various masses. These lenses are dim but emit some light, so after the lensing event ends and the lens moves away from the line of sight to the background star, you can sometimes detect the lens directly. But for OGLE 2011BLG0462, no lens light was detected even in the deep Hubble images. The lens was completely dark. This absence of light ruled out main sequence stars and white dwarfs immediately. A 7 solar mass main sequence star would be a brilliant blue-white O-type star, easily visible at 5,000 light-years distance. A white dwarf could be darker, but can't have 7 solar masses. White dwarfs max out at about 1.4 solar masses, the Chandrasekhar limit, above which electron degeneracy pressure can't support the star against gravity. The only stellar remnants that can have 7 solar masses and emit no light are neutron stars and black holes. Neutron stars, however, often emit radiation. Young neutron stars spin rapidly and emit beams of radio waves from their magnetic poles, appearing as pulsars if those beams sweep across Earth. Older neutron stars that have spun down still emit X-rays from their hot surfaces, gradually cooling over millions of years but remaining detectable. Deep X-ray observations of the OGLE 2011BLG0462 position with the Chandra X-ray Observatory detected nothing. No radio pulsations, no X-ray glow, no light at any wavelength. Combined with the 7 solar mass measurement well above the neutron star maximum, the conclusion was inescapable. This was a black hole. The bending of light that revealed this invisible object wasn't just a theoretical prediction, confirmed it was a practical tool for discovering objects that would otherwise remain forever hidden. Every photon from the background star that reached Earth during the lensing event had its trajectory altered by passing through curved spacetime around the black hole. Photons passing on one side of the black hole bent one way, those passing on the other side bent the opposite way. The net result? More photons reached Earth than would have without the lens, and they arrived from slightly different angles than the star's true position, creating both magnification and displacement. This technique, gravitational microlensing, has become one of astronomy's most powerful tools for detecting dark objects. Unlike electromagnetic observations that require the target to emit or reflect light, microlensing works for anything with mass. Black holes, brown dwarfs, free-floating planets, neutron stars, white dwarfs, all can be detected through their gravitational influence alone. The OGLE survey alone has detected over 20,000 microlensing events since 1992, though most are caused by ordinary stars. Identifying the rare events caused by black holes requires the detailed follow-up that Hubble provides, separating the invisible lenses from the merely dim ones, the 7 solar mass object moving at 45 kilometers per second. The mass measurement of 7.1 solar masses for OGLE 2011BLG0462 comes from combining 3 independent observables: the duration of the lensing event, the amplitude of the centroid shift, and the shape of the light curve. Each measurement constrains different aspects of the lens's properties, and together they determine mass, distance, and velocity simultaneously through the lens equation formalism in general relativity. The 270-day duration tells you about the Einstein radius crossing time. A more massive lens creates a larger Einstein radius, the circle on the sky where light rays are bent by the gravitational field. If the lens moves at a given velocity, the time to cross this circle scales with the square root of the mass. But duration alone doesn't give you mass because you don't know the velocity independently. A massive lens moving slowly produces the same duration as a lighter lens moving faster. The centroid shift breaks this degeneracy. The magnitude of the position displacement depends on the angular Einstein radius, which depends on mass and distance, but not on velocity. A more massive or closer lens produces a larger angular Einstein radius, and thus a larger centroid shift. The measured 2.82 milliarc-second shift immediately constrains the combination of mass and distance. For the measured distance of 5,150 light-years, this shift corresponds to a 7 solar mass lens. The light curve shape provides additional information. Gravitational lensing magnification depends on how close the lens passes to perfect alignment with Earth and the background star. The impact parameter, the minimum angular separation between lens and source during the event, determines the peak magnification. For OGLE 2011BLG 0462, the impact parameter was about 0.5 Einstein radii, meaning the lens passed the background star at a distance equal to half the Einstein radius. This intermediate impact parameter produced moderate magnification of about 300 times the unlensed brightness at peak. From these measurements, the lens's velocity through space emerges. The black hole is moving at 45 kilometers per second relative to the background star. Since the background star is in the galactic bulge and presumably orbits the galactic center at roughly 220 kilometers per second, like most stars at that location, while stars in the local disk where the black hole resides orbit at similar speeds, the 45 kilometers per second represents the peculiar velocity, the deviation from average circular motion for objects at that location. This velocity is unusually slow for an ejected black hole. If a supernova explosion is highly asymmetric, with more ejecta thrown in one direction than others, the recoil can kick the nascent black hole to velocities of several hundred kilometers per second. Observed pulsars, which are neutron stars that received kicks during their formation supernovae, show velocities ranging from 100 to over 1,000 kilometers per second. The famous pulsar PSRB 1000, 508 plus 55 moves at 1,100 kilometers per second, fast enough to escape the Milky Way entirely if it's headed in the right direction. If the OGLE black hole received only a 45 km per second kick, the supernova must have been relatively symmetric. Or perhaps the black hole didn't form in a supernova at all. Some massive stars are thought to collapse directly to black holes without a supernova explosion when their cores are so massive that the collapse proceeds smoothly rather than bouncing and exploding. These direct collapse black holes would receive no kick, maintaining whatever velocity the progenitor star had. The 5,150 light-year distance places the black hole in the Milky Way's thin disk, the flattened region about 1,000 light-years thick, where most stars, gas, and dust reside. This is where massive stars form and where supernovae occur. The black hole hasn't escaped the disk. Despite being 10 to 100 million years old, the typical age for a black hole formed from a 2.5 solar mass star. At 45 kilometers per second, it takes about 100 million years to travel 5,000 light-years. If the black hole formed nearby and has been wandering since, it could have traveled that distance in its lifetime. But there's another possibility. The black hole formed farther away and has been traveling toward us, or it formed closer and is now heading away. The measured velocity is the transverse velocity motion perpendicular to our line of sight. Radial velocity motion toward or away from us doesn't affect the lensing duration or centroid shift, so it remains unknown. The black hole could have a substantial radial velocity component that we can't measure through microlensing alone. Spectroscopy could reveal radial velocity if the black hole had a companion star, but it doesn't. It's moving through space in 3 dimensions, and we only know 2 of those dimensions. The mass measurement also has implications for the black hole's formation. 7 solar masses is on the lower end of the stellar black hole mass distribution. Most black holes detected in X-ray binaries have masses between 5 and 15 solar masses, with a few outliers up to 20 solar masses. The lower mass black holes likely formed from slightly less massive progenitor stars that underwent supernovae with more vigorous explosions, ejecting more mass and leaving behind smaller remnants. A 7 solar mass black hole probably formed from a star with initial mass around 20 to 25 solar masses. These progenitor star masses are common. Stars with masses 20 to 25 solar masses represent a sizable fraction of all massive star formation. If a typical fraction of these stars form black holes rather than neutron stars, and if a typical fraction of those black holes are ejected from their birth locations to wander alone rather than remaining in binaries or clusters, then the Milky Way should contain millions of solitary black holes like OGLE 2011b LG 0462. Most will never reveal themselves because they'll never happen to pass in front of a background star that we're monitoring. But a few, like this one, will announce their presence through the telltale signature of gravitational lensing. The uncertainty in the mass 6, 0 to 8.4 solar masses at 95% confidence, reflects the measurement uncertainties in the observables and the assumptions about distances. The background star's distance is estimated from its color and brightness, assuming it's a typical main sequence star in the bulge at roughly 27,000 light-years. The lens distance comes from combining the measured angular Einstein radius with the implied physical Einstein radius from the event duration. These distances have uncertainties of 10 to 20%, which propagate into the mass estimate. But even accounting for these uncertainties, the mass is well above the neutron star limit and firmly in black hole territory. There's no ambiguity about what this object is. It's a black hole, a region of space-time where gravity is so strong that escape velocity exceeds the speed of light, creating an event horizon from which nothing can escape. With 7 solar masses compressed into an infinitesimal point, the Schwarzschild radius, the radius of the event horizon, is about 20 kilometers. If you could somehow see the black hole directly, it would appear as a perfectly black sphere 40 kilometers in diameter, surrounded by a shadow slightly larger due to light bending around the horizon. But you can't see it directly because it's black. No light escapes. The only way we know it exists is because it passed in front of a background star and bent spacetime enough to magnify that star's light for 270 days. Without that chance alignment, we would never know the black hole was there. Its invisible, silent, darker 7 solar mass pocket of warped spacetime drifting through the galactic disk at 45 kilometers per second, going nowhere in particular, alone in the darkness between the stars. The galactic bulge, where millions of stars hide cosmic ghosts. The galactic bulge is the Milky Way's dense central region, a roughly spherical distribution of stars, about 10,000 light-years in diameter, centered on the galactic nucleus. Unlike the flat disk where the Sun resides, the bulge is 3-dimensional and thick, containing about 10 to 20 billion stars, roughly 10% of the galaxy's total stellar population. These stars are predominantly old, formed 10 to 13 billion years ago in the early universe, when star formation rates were much higher than today. From Earth's perspective, 27,000 light-years from the galactic center, looking toward the bulge means looking through the disk, through layers of dust and gas that absorb and scatter light, particularly at visible wavelengths. This interstellar dust, composed of tiny grains of carbon and silicate minerals, dims starlight by several magnitudes. A star in the bulge that would appear bright if the line of sight were clear instead appears faint and red, with much of its blue and ultraviolet light absorbed. Only infrared light penetrates the dust relatively unimpeded, which is why infrared telescopes are essential for studying the bulge. Despite the obscuration, the bulge is prime territory for microlensing searches. The high stellar density means millions of background stars are available as potential sources for lensing events. The distance far enough that the disk's foreground stars can act as lenses, creating alignments, makes it likely that lenses will pass in front of background bulge stars. And the three-dimensional structure means that at any given moment, many stars are nearly perfectly aligned, just waiting for a lens to drift into place. The Optical Gravitational Lensing Experiment began surveying the galactic bulge in 1992, using a 1.3-meter telescope at Las Campanas Observatory in Chile's Atacama Desert. OGLE pioneered the technique of monitoring millions of stars nightly, looking for the characteristic symmetric brightening that signals lensing. The survey was led by Polish astronomer Andrzej Judalski at the University of Warsaw, who recognized that while individual lensing events are rare, monitoring enough stars makes them routine. OGLE images a region of sky about 40 square degrees, roughly 200 times the area of the full moon, covering much of the galactic bulge. Within this region, the survey tracks about 200 million individual stars, measuring their brightness in multiple filters every few nights throughout the observing season. This generates about 2 terabytes of data per year. Automated software scans the light curves of all these stars, flagging any that show the smooth, symmetric brightening characteristic of microlensing. In a typical year, OGLE detects about 2,000 microlensing events. Most last 10 to 30 days, caused by red dwarfs or white dwarfs in the disk passing in front of bulge stars. A small fraction, perhaps 5%, last longer than 100 days, indicating either more massive lenses or slower velocities. These long-duration events are of special interest because they're more likely to be caused by black holes or neutron stars, both of which are more massive than typical stars and thus create larger Einstein radii that take longer to cross. The Microlensing Observations in Astrophysics Collaboration, MOA, operates independently but monitors much of the same sky. MOA uses a 1.8-meter telescope at Mount John Observatory in New Zealand, giving it a view of the galactic bulge during the southern hemisphere's winter when the bulge is high in the night sky. MOA's observing strategy differs slightly from OGLE: higher cadence but fewer filters, but the goal is the same: catch as many microlensing events as possible. When both OGLE and MOA independently detect the same event, confidence increases dramatically. Systematic errors or instrumental artifacts that might fool one survey are unlikely to fool both. For OGLE 2011b, LG0462/M, OA 2011b, LG191, both teams independently identified the event within days of its start, confirmed the brightening pattern matched microlensing, and alerted the astronomical community. This triggered follow-up observations with larger telescopes, including the crucial Hubble Space Telescope observations that measured the astrometric displacement. The galactic bulge is more than just a convenient background screen. It's a fossil record of the Milky Way's early history. Unlike the disk, where ongoing star formation continuously creates new stars, the bulge has been quiescent for billions of years. Its stars preserve chemical compositions from the early universe, lower metallicities than solar, with less iron and heavy elements, because fewer generations of stars had lived and died to enrich the interstellar medium. Studying the bulge reveals what conditions were like when the galaxy was young, but the bulge also contains dark objects. For every visible star, there are stellar remnants, white dwarfs from low-mass stars that died, neutron stars from intermediate-mass stars that went supernova, and black holes from the most massive stars. These remnants outnumber living stars by perhaps 10 to 20%, contributing significantly to the lens population. When a lensing event occurs, the lens could be a living star in the disk Or it could be a dead star, a white dwarf, neutron star, or black hole drifting through the disk after its formation. The distribution of these remnants throughout the galaxy isn't uniform. Young massive stars form preferentially in spiral arms, where gas concentrations are high. When these stars die and leave black holes, those black holes initially cluster in the spiral arms, but over millions of years, gravitational interactions with other stars and random motions disperse them throughout the disk. Older black holes, from stars that died billions of years ago, have had time to wander far from their birthplaces, creating a smoother distribution throughout the galactic disk. Some black holes fall toward the galactic center, pulled by the gravitational potential well created by the central supermassive black hole Sagittarius A star. This process, called dynamical friction, causes massive objects to lose orbital energy and spiral inward over time. Simulations suggest that thousands of stellar mass black holes have accumulated within a few light years of Sagittarius A star, forming a dense cluster around the supermassive black hole. These central black holes are invisible individually, but contribute to the dynamical mass measured in that region. For microlensing surveys, the galactic bulge offers another advantage. It's relatively close on cosmic scales. At 27,000 light-years, the bulge is about a third of the way across the galaxy, but close enough that even dim stars are detectable with modest telescopes. Compare this to extragalactic microlensing searches that target the Magellanic Clouds at 160,000 light-years, or M31 at 2.5 million light-years. The closer the target field, the more stars can be monitored, and the more lensing events will be detected. OGLE has detected over 20,000 microlensing events since 1992, and MOA has detected thousands more. The vast majority are caused by ordinary stars, red dwarfs comprising 70% of all lenses, higher mass main sequence stars comprising another 20%, and white dwarfs perhaps 5%. Neutron stars and black holes together probably cause less than 1% of events, but with 20,000 events total, that 1% means 200 events potentially caused by compact objects. Identifying which ones requires the detailed follow-up that separates the dark lenses from the merely dim ones. The galactic bulge isn't just hiding black holes. It's hiding everything dark. Brown dwarfs too light to sustain fusion, rogue planets ejected from their planetary systems, white dwarfs cooled to invisibility, neutron stars with no pulsations. Each of these objects can cause microlensing, and each requires careful analysis to distinguish from the others. The black holes stand out by their masses. 7 solar masses is too heavy for anything but a black hole. But 2 solar mass lenses could be neutron stars or black holes, requiring additional observations to distinguish. 0.5 solar mass lenses could be white dwarfs, red dwarfs, or brown dwarfs. The galactic bulge microlensing surveys are inadvertently conducting a census of all dark objects in the galaxy, one gravitational lens at a time. The 3 possible origins of a homeless black hole. Stellar mass black holes form inside massive stars when those stars exhaust their nuclear fuel. A star with initial mass above, about 20 to 25 solar masses, develops an iron core that grows until it exceeds the Chandrasekhar limit, about 1.4 solar masses, at which point electron degeneracy pressure can no longer support the core against gravity. The core collapses in less than a second, releasing gravitational binding energy of order 10 to the 53rd power ergs, or about 100 times the Sun's total luminosity over its 10 billion year lifetime in a few seconds. Most of this energy escapes as neutrinos, which barely interact with matter and stream freely from the collapsing core. But a small fraction, around 1%, gets deposited in the star's outer layers, driving a shockwave that blows those layers off in a supernova explosion. If all goes well, the explosion is symmetric, the ejecta fly off equally in all directions, and the remnant, either a neutron star or black hole, remains at the explosion site with essentially zero velocity relative to the progenitor star's motion. But supernovae aren't always symmetric. Detailed computer simulations of core collapse supernovae by groups at Oak Ridge National Laboratory, the Max Planck Institute for Astrophysics, and Princeton University show that the explosion develops instabilities. Convective overturn creates hot and cool regions in the material just outside the nascent neutron star. Asymmetries in the collapse itself, perhaps due to rapid rotation or magnetic fields, create preferred directions. The result: more ejecta fly off in some directions than others. This asymmetry creates recoil. Conservation of momentum demands that if more mass flies off to one side, the remnant must recoil in the opposite direction. The magnitude of the kick depends on the degree of asymmetry and the total mass ejected. If 10 solar masses of material is ejected and the asymmetry is 10%, meaning 5.5 solar masses goes one direction and 4.5 goes the other, the momentum difference accelerates the 1.5 solar mass remnant to about 400 kilometers per second. Observations of pulsars provide direct evidence for supernova kicks. Pulsars are neutron stars with strong magnetic fields and rapid rotation, emitting beams of radio waves from their magnetic poles. As the neutron star spins, these beams sweep across space like a lighthouse, and if a beam points toward Earth, we detect regular pulses. The periods are extraordinarily stable. Some pulsars tick like atomic clocks, allowing precise measurements of their positions and velocities through astrometry and timing. The pulsar population shows a wide range of velocities. The average is about 400 kilometers per second, but the distribution is broad. Some pulsars move at 100 kilometers per second. Others exceed 1,000 kilometers per second. The famous pulsar PSR J2 plus 6216, discovered in 2017, moves at 1,130 kilometers per second, fast enough to escape the Milky Way entirely. It was born in a supernova remnant called CTB-1, and in the 10,000 years since the explosion, it has traveled 53 light-years. From the remnant, the kick velocity was so high that it's now far from its birthplace. If neutron stars receive kicks, black holes should too. The formation mechanism is similar asymmetric core collapse, creating asymmetric explosions. But there's a complication. Black holes form from more massive stars that may undergo different explosion dynamics. Some models suggest that very massive stars collapse directly to black holes without a visible supernova, in which case there's no explosion asymmetry and no kick. Other models suggest that the fallback of material onto the nascent black hole after the initial explosion provides additional asymmetry and kicks. The second mechanism for creating isolated black holes is binary black hole mergers. When two black holes orbit each other, they emit gravitational waves ripples in space-time that carry energy and angular momentum away from the system. This emission causes the orbit to decay, bringing the black holes closer together. Eventually they merge, forming a single black hole. But if the merger is asymmetric, if the two black holes have unequal masses or spins pointing in different directions, the gravitational waves are emitted preferentially in some directions rather than uniformly, creating recoil. The recoil velocity depends on the mass ratio and spin configurations. For equal mass mergers with spins aligned, the recoil is small, typically 10 to 100 kilometers per second. But for unequal masses or anti-aligned spins, the recoil can reach 500 to 1,000 kilometers per second. In the most extreme configurations, black holes with high spins pointing in opposite directions, theoretical calculations predict kick velocities up to 5,000 kilometers per second, fast enough to escape any galaxy. LIGO and Virgo have detected dozens of binary black hole mergers since the first detection in 2015. The famous event GW150914 involved black holes with masses 36 and 29 solar masses merging to form a 6-2 solar mass remnant, with 3 solar masses converted to gravitational wave energy. According to Einstein's equation, E equals mc squared. The mass ratio, about 1.2 to 1, produced a modest kick velocity, estimated at 170 kilometers per second. The merger product remained bound to its host galaxy, but GW190521, detected on the 21st of May 2019, was different. This merger involved black holes with masses 85 and 66 solar masses, forming a 142 solar mass remnant. Both progenitor black holes were in the pair instability supernova gap, the mass range from 50 to 130 solar masses, where stars are thought to be unable to leave black hole remnants, because pair instability supernovae completely disrupt them. The existence of these black holes challenges formation theories, and the merger's asymmetry produced a kick velocity estimated at 1,500 kilometers per second, potentially ejecting the remnant from its host environment. If such kicked black holes are common, some should be wandering through the Milky Way. The merger rate in the galaxy, extrapolated from LIGO/Virgo detections, is about 10 to 100 per million years. Over the galaxy's 10 billion year lifetime, that's 100,000 to 1 million mergers. If 10% of these produce kick velocities above 500 kilometers per second, there should be 10,000 to 100,000 ejected merger remnants roaming the galaxy. Most would have escaped to intergalactic space, but some would remain gravitationally bound, slowly orbiting through the halo and occasionally passing through the disk where they could be detected through microlensing. The third mechanism is ejection from dense star clusters. Globular clusters, ancient spherical collections of hundreds of thousands to millions of stars packed into regions 100 light-years across, are dynamical cauldrons. Stars repeatedly pass close to each other, exchanging energy and momentum through gravitational interactions. Occasionally, a close encounter between 3 objects, say 2 black holes, and a star results in one object being flung out of the cluster at high velocity, while the other 2 become more tightly bound. Computer simulations of globular cluster dynamics by Frederick Razio's group at Northwestern University show that black holes, being more massive than average stars, tend to segregate toward cluster centers through dynamical friction, the same process that causes massive objects to spiral toward the galactic center. These central black holes then interact frequently, forming binaries that harden through 3-body encounters. Eventually, some black holes gain enough energy to escape the cluster entirely, ejected at velocities of 50 to 500 kilometers per second. Observations support this picture. Several globular clusters show evidence for black holes through dynamical studies. In NGC 3201, a globular cluster 16,000 light-years away, astronomers detected a star orbiting an invisible companion with a mass of 4.36 solar masses, a black hole. The system is inside the cluster, suggesting black holes remain in clusters despite dynamical ejections. But the presence of black holes in clusters implies that some have been ejected, contributing to the population of wandering black holes in the galactic halo and disk. For OGLE 201 1BLG0462, the 45 km per second peculiar velocity is consistent with any of these mechanisms. A modest supernova kick could produce this velocity. A low mass ratio binary merger could produce it. Ejection from a globular cluster could produce it. Without additional information such as the black hole's trajectory, age, or association with any remnant structure distinguishing the mechanisms is difficult. The black hole could have formed 10 million years ago in a supernova, received a small kick, and been wandering ever since. Or it could have formed billions of years ago in a cluster, been ejected, and has been orbiting through the galaxy for eons. the supernova explosion that launched a corpse into space. When a massive star runs out of nuclear fuel, its fate is sealed. The star has spent millions of years fusing hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, and so on up the periodic table, each fusion stage happening faster and releasing less energy per reaction. The final stage, silicon fusion to iron, takes only a few days. Once the core contains about 1.4 solar masses of iron, no further fusion is possible because iron is at the peak of the nuclear binding energy curve. Fusing iron requires energy input rather than releasing it. Without fusion pressure to support it, the iron core collapses. Gravity pulls the core inward, compressing it to densities comparable to atomic nuclei, about 10 to the 14th power grams per cubic centimeter. At these densities, electrons and protons are squeezed together, combining to form neutrons and neutrinos in a process called neutronization. The neutrinos escape, carrying away energy and cooling the core further, accelerating the collapse. In less than 1 second, the core shrinks from 3,000 kilometers radius to 30 kilometers radius, a compression factor of 100 inches radius, or 1 million in volume. The collapse halts when the core reaches nuclear density and neutron degeneracy. Pressure. The quantum mechanical resistance of neutrons to being squeezed becomes strong enough to support the core. The abrupt halt creates a shock wave that propagates outward through the infalling outer layers. This shock wave should, in theory, blow off the star's envelope, producing a supernova. But detailed simulations show that the shock wave stalls about 100 to 200 kilometers from the core, losing energy to photodissociation of iron nuclei and neutrino losses. What revives the stalled shock is neutrino heating. The collapsing core produces a burst of neutrinos with energies around 10 million electron volts. Although neutrinos interact very weakly with matter, the densities are so high that about 1% of the neutrino energy gets deposited in the material just behind the stalled shock. This heating revives the shock, pushing it outward again. The revived shock accelerates through the star's outer layers, taking hours to days to reach the stellar surface and blow it off in a supernova explosion visible across millions of light years. But the neutrino heating isn't uniform. Convection develops in the region between the neutron star and the shock-hot material rises. Cool material falls, creating turbulent eddies. These convective eddies are visible in modern 3D simulations as enormous rising plumes of hot neutrino-heated material breaking through the shock in some directions, while cooler material falls back in others. The result, the explosion, is asymmetric. More energy is deposited in some directions than others, and more ejecta flies off in some directions. This asymmetry gives the neutron star a kick. If 10 solar masses of ejecta flies off and 10% more mass goes to the north than the south, the momentum imbalance kicks the 1.4 solar mass neutron star southward at several hundred kilometers per second. The exact velocity depends on the degree of asymmetry and the total ejecta mass. But typical simulations produce kick velocities between 100 and 1000 kilometers per second, matching the observed pulsar velocity distribution. Christy Ning and Tugulda Sukbold at Ohio State University ran 3D supernova simulations in 2018 that showed kicks are essentially universal. Nearly all core collapse supernovae produce kicks, though the magnitude varies. Stars with rapid pre-collapse rotation produce stronger kicks because rotation breaks spherical symmetry. Stars with strong magnetic fields also produce stronger kicks because magnetic fields guide the explosion asymmetry. But even slowly rotating, weakly magnetized stars produce some kick due to the inherent turbulence of the neutrino-driven explosion mechanism. For black hole formation, the situation is more complex. If the progenitor star is massive enough, perhaps above 25 to 30 solar masses, the core collapse may not produce a supernova at all. After the initial bounce, so much material falls back onto the neutron star that it exceeds the maximum neutron star mass, about 2.5 solar masses, and collapses further to form a black hole. The infalling material swallows the neutron star, extinguishing any potential supernova before the explosion can fully develop. These direct collapse events are called failed supernovae, and they're believed to be common for the most massive stars. Failed supernovae should produce minimal kicks because there's no asymmetric explosion to create recoil. The black hole forms quietly, inheriting whatever velocity the progenitor star had. But recent theoretical work by Bernhard Müller at Monash University suggests that even failed supernovae can produce kicks through asymmetric fallback. If the material falling back onto the nascent black hole is asymmetric, perhaps due to rotation or magnetic fields, the angular momentum and momentum imbalance can give the black hole a modest kick of 10 to 50 kilometers per second, even without a visible explosion. Observationally, there's evidence for kicked black holes. Cygnus X1, the first black hole candidate discovered, is moving at about 20 kilometers per second relative to the local standard of rest, the average motion of stars in its region of the galaxy. By tracing this motion backward, astronomers found that Cygnus X1 was born in the Cygnus OB3 Association, a group of young massive stars about 6,000 light-years away. The black hole received a small kick during formation and has been drifting away from its birth association for about 5 million years. Another example is GRO J1000, 655-40, a black hole X-ray binary discovered by the Compton Gamma Ray Observatory in 1994. The black hole has a mass of about 6 solar masses and is in a binary with a low-mass star, but the system is moving at 112 kilometers per second through the galaxy, much faster than typical stars in its location. Tracing backward, the binary was likely born in the Scorpius-Centaurus Association and received a kick that ejected it about 100 million years ago. The binary survived the kick, but many companions likely don't. The sudden acceleration when the primary explodes can disrupt the binary, leaving the black hole alone. The fraction of black holes that end up isolated depends on the binary fraction among massive stars and the binary survival rate. Observations suggest about 70% of massive stars are in binary systems. If supernova kicks disrupt 50% of these binaries, about 85% of all stellar mass black holes end up isolated, 30% because they formed from single stars, plus 35% because their binaries were disrupted. The remaining 15% stay in binaries and become the X-ray binaries we detect through their accretion disk emission. For OGLE 2011b LG0462, the 45 km per second peculiar velocity is slower than typical supernova kicks, but consistent with the low end of the distribution, or with a failed supernova producing a modest kick. If the black hole formed 10 million years ago with a 45 km per second kick, it has travelled about 1,500 light-years from its birthplace. Any stellar association or cluster where it formed has likely dispersed in that time, explaining why no cluster is visible at the black hole's current location. The supernova that created this black hole, if there was one, would have been visible across the galaxy when it occurred. A typical core collapse supernova reaches a peak luminosity about 1 billion times the Sun's luminosity, bright enough to be visible to the naked eye from thousands of light-years away for a few months. If the event happened 10 million years ago, no human witnessed it. Homo sapiens didn't exist yet. But the light from that explosion, if it occurred, has long since passed Earth, carrying away the announcement of the black hole's birth that no one was there to see. The gravitational wave recoil that flings black holes away. When two black holes orbit each other, they lose energy and angular momentum by emitting gravitational waves ripples in space-time predicted by Einstein's general relativity. These waves carry energy away from the system at a rate proportional to the sixth power of the orbital velocity and inversely proportional to the fifth power of the orbital radius. For stellar mass black holes orbiting at moderate distances, the energy loss is tiny and the orbital decay takes millions of years. But as the orbit shrinks, the process accelerates. In the final seconds before merger, the black holes spiral inward at a significant fraction of light speed, emitting gravitational waves so powerful that they carry away several solar masses of energy, according to E=mc². LIGO made the first direct detection of gravitational waves on the 14th of September 2015 from an event designated GW150914. Two black holes with masses 36 and 29 solar masses merged 1.3 billion light-years from Earth, releasing 3 solar masses of energy as gravitational waves in the final 0.2 seconds before merger. The waves strain in space-time of order 10 to the negative 21st power changed the separation between LIGO's mirrors by about 1,000th the diameter of a proton. Yet LIGO detected them clearly, marking the beginning of gravitational wave astronomy. The merger didn't just create gravitational waves, it created a kick. The two black holes had unequal masses, and their spins weren't perfectly aligned with the orbital angular momentum. As they spiraled inward, the gravitational waves they emitted carried away momentum in a preferred direction, rather than uniformly in all directions. When the black holes merged, the resulting 6.2 solar mass black hole recoiled at 170 kilometers per second, fast enough to remain bound to its host galaxy, but moving at several times the galaxy's escape velocity from a dwarf galaxy. The recoil velocity depends on several factors. For black holes with equal masses and spins aligned with the orbit, the symmetry of the merger produces minimal recoil, perhaps 10 to 20 kilometers per second. But if the masses are unequal, more gravitational waves are emitted in the direction of the less massive black hole, kicking the merger product toward the more massive black hole's original position. The kick velocity scales roughly as the square of the mass ratio multiplied by some function of the spins. Manuela Campanelli and Carlos Lausto at Rochester Institute of Technology performed detailed numerical simulations in 2007, showing that the maximum kick velocity occurs for mass ratios around 2:1 or 3:1. For equal masses, the kick is small due to symmetry. For very unequal masses, say 10:1, the kick is also small, because the lighter black hole contributes little momentum to the system. The sweet spot for maximum kicks is intermediate mass ratios with spins anti-aligned or perpendicular to the orbit, producing recoils up to 5,000 kilometers per second. These superkicks could eject black holes from dwarf galaxies entirely. The Milky Way's escape velocity at the solar neighborhood is about 550 kilometers per second. For dwarf galaxies with masses 100 to 1,000 times smaller than the Milky Way, escape velocities are 50 to 200 kilometers per second. A black hole merger producing a 500 kilometers per second kick would escape any dwarf galaxy and likely escape even from the outskirts of a large galaxy like the Milky Way if the merger occurred far from the galactic center. Some ejected black holes have been found. In 2017, astronomers using the Chandra X-ray Observatory discovered a source designated CXO J101527 2 + 625,911 inches, a galaxy 3.9 billion light-years away. The source was offset by 13,000 light-years from the galaxy's center, moving at 1,600 kilometers per second, too fast to remain bound. X-ray spectroscopy showed emission from hot gas around a black hole accreting at a high rate, with a mass estimated at 160 million solar masses. The leading explanation: this is the recoiling remnant of a supermassive black hole merger kicked out of the galaxy core and now escaping into intergalactic space. For stellar mass black holes, identifying merger remnants is harder because they don't have luminous accretion disks unless they're in dense environments or binaries. A stellar mass black hole kicked to 500 kilometers per second and wandering alone through the galactic halo would be essentially invisible unless it happened to pass in front of a background star and create a microlensing event. Gravitational wave observations provide an indirect census. LIGO and Virgo have detected about 90 binary black hole mergers as of 2024, implying a merger rate in the local universe of about 10 to 100 per gigaparsec cubed per year. Integrated over cosmic time, this produces an enormous population of merger remnants. Not all merger remnants are ejected. Most receive kicks below 100 kilometers per second, keeping them bound to their host galaxies, but even a bound kicked black hole becomes effectively isolated. If it formed in a galaxy's halo at 50 kiloparsecs from the center and received a 200 kilometers per second kick, it might take 500 million years to fall back toward the galactic center. During that time, it's wandering the halo, occasionally passing through the disk, and could lens background stars, just like OGLE 201, 1BL G0462. The spin configurations of merging black holes determine kick magnitude and direction. Black holes can have spins up to the maximum allowed by general relativity, a dimensionless spin parameter of 1, corresponding to angular momentum equal to the square of the black hole's mass times Newton's gravitational constant divided by the speed of light. Mergers between black holes with high spins pointing in the same direction as the orbital angular momentum produce small kicks, but mergers with spins anti-aligned or perpendicular produce large kicks. LIGO and Virgo measure spins indirectly through the gravitational waveform. As black holes spiral inward, spin-orbit coupling causes the orbital plane to precess wobble like a spinning top. This precession imprints modulations on the gravitational wave frequency and phase, allowing extraction of information about the spins. For GW 150914, both black holes had low to moderate spins with some misalignment, producing the observed 170 km per second kick. For GW 190521, the spins were higher and more misaligned, producing an estimated 1,500 km per second kick. The fate of kicked merger remnants depends on their environments. In galaxy clusters, where galaxies orbit through a hot intracluster medium at velocities of 500 to 1,000 km per second, even a super-kicked black hole might remain bound to the cluster even if it escapes its host galaxy. These wandering cluster black holes would accumulate over billions of years as successive mergers eject remnants. Eventually, clusters might contain hundreds of wandering black holes drifting through the intra-cluster space, occasionally accreting hot gas and briefly becoming visible as X-ray sources. In the field regions of the universe, away from clusters, kicked black holes become truly isolated. Intergalactic space contains almost no gas, so accretion is negligible. The black holes simply drift through the cosmic void, invisible and undetectable except through rare microlensing events. Over billions of years, cosmic expansion carries them farther from their host galaxies. Eventually, they're so far from other matter that they'll never encounter another star or accrete another particle. They become permanent cosmic orphans, wandering the empty spaces between galaxy clusters. For OGLE 2011BLG0462, could it be a merger remnant? The 7 solar mass is consistent with stellar mass merger products detected by LIGO, which range from 35 to 150 solar masses. Weight 35 is much larger than 7. Most LIGO mergers involve black holes more massive than 7 solar masses. A merger producing a 7 solar mass remnant would require progenitors with masses around 4 and 4 solar masses, both at the low end of the black hole mass distribution and possibly in the mass gap between neutron stars and black holes. Such a merger hasn't been detected yet, though it's possible. More likely, OGLE 2011b LG0462 formed through core collapse supernova, not merger. The 7 solar mass is typical for first-generation black holes from massive star collapse. The 45 km per second velocity is too slow for a typical merger kick, though not impossible if the merger had favorable mass ratios and spin configurations. The absence of any companion or environment supports an old, isolated black hole that's been wandering for millions of years since formation, rather than a recent merger product still associated with its formation environment. The most parsimonious explanation: this is a supernova remnant that received a modest kick and has been drifting ever since. The dense star clusters, where black holes play billiards. Globular clusters are ancient spherical collections of stars, fossils from the early universe when the Milky Way was forming 12 to 13 billion years ago. Unlike the flat disk where most stars reside, globular clusters are three-dimensional balls containing anywhere from 100,000 to several million stars, packed into regions only 100 to 200 light-years across. The Milky Way has about 150 known globular clusters orbiting through the galactic halo, and each one is a dynamical laboratory where gravity orchestrates complex interactions impossible anywhere else. The cluster 47 Tucanae, visible to the naked eye from the southern hemisphere as a fuzzy star in the constellation Tucana, contains about 1 million stars in a sphere 120 light-years in diameter. That's a stellar density about 1,000 times higher than in the solar neighborhood. In the cluster's core, where density peaks at 10,000 times the local stellar density, the average distance between stars is only 0.1 light-years, about 6,000 astronomical units. For comparison, the nearest star to our Sun is 4.2 light-years, or 270,000 astronomical units away. In 47 Tucanae's core, stars are 45 times closer on average. This crowding creates frequent close encounters. Stars don't collide even in the densest cores. The chance of direct collision is negligible because stars are tiny compared to the space between them. But gravitational encounters are common. When two stars pass within a few stellar radii of each other, their mutual gravity alters their trajectories, exchanging energy and momentum. Over millions of close encounters, these interactions redistribute energy throughout the cluster, with some stars gaining energy and moving outward, while others lose energy and sink toward the center. This process, called mass segregation, causes more massive objects to sink toward the cluster center through a mechanism analogous to friction. A massive star moving through the cluster experiences countless tiny gravitational tugs from passing stars. Each encounter transfers a small amount of kinetic energy from the massive star to the lighter stars. Over time, the massive star slows down and spirals inward, while the lighter stars speed up and move outward. The timescale for this process, called the dynamical friction timescale, is roughly 1 billion years for solar mass stars, but only 100 million years for 10 solar mass objects. Black holes, being the most massive objects in clusters, segregate to the center fastest. Simulations by Fabio Antonini at Cardiff University show that stellar mass black holes with masses 5 to 20 solar masses sink to the cluster core within 100 million years of formation. Once there, they dominate the central dynamics. The cluster core becomes a black hole subsystem where black holes interact primarily with each other rather than with stars, forming binaries through three-body encounters and exchanging energy through gravitational slingshots. Three-body encounters work like this. Two black holes in a binary orbit each other with some binding energy. A third black hole approaches and interacts gravitationally with the binary. During the chaotic encounter, one of three outcomes occurs. First, the interloper might steal energy from the binary, making the binary tighter and getting ejected at high velocity, a gravitational slingshot. Second, the interloper might replace one member of the binary, ejecting that member while becoming bound to the remaining member. Third, the binary might break apart, with all three black holes flying off in different directions. The most common outcome is the first. The binary hardens while the interloper is ejected. With each encounter, the binary's binding energy increases, meaning the two black holes orbit more tightly. Eventually, the binary becomes so tight that gravitational wave emission dominates the evolution, causing the black holes to merge within millions of years. But the encounters also eject black holes from the cluster. Simulations show that after 10 to 100 three-body encounters involving a given binary, one black hole gets ejected with enough velocity to escape the cluster. The escape velocity from globular clusters varies with cluster mass and size. For 47 Tucanae, the escape velocity from the center is about 50 kilometers per second. For lower mass clusters like NGC 6397, which contains only 100,000 stars, the escape velocity is 20 kilometers per second. Black holes participating in three-body encounters often acquire velocities exceeding escape velocity, especially if they're in the tail of the velocity distribution after many encounters. These black holes leave the cluster and wander into the galactic halo. Observations confirm black holes exist in globular clusters. In 2017, astronomers using the Muse spectrograph on the Very Large Telescope in Chile studied NGC 3201, a globular cluster 16,000 light-years away. By measuring velocities of individual stars through Doppler shifts of their spectral lines, they detected a star orbiting an invisible companion every 167 days. The orbital velocity, 240 km per second, implied a companion mass of 4.36 solar masses. Too massive for a neutron star, too dim for any main sequence star or white dwarf. It had to be a black hole. The discovery proved black holes remain in clusters despite dynamical ejections. But it also implies many have been ejected. If NGC 3201 contains one detectable black hole, it likely contains several undetected ones, perhaps 10 to 100 total. Over the cluster's 1-2 billion-year lifetime, hundreds more may have formed and been ejected. Each ejection sends a black hole into the galactic halo at 20 to 100 kilometers per second, depending on cluster properties and encounter specifics. Some ejected black holes fall back toward the galactic disk through the halo's gravitational potential. A black hole ejected from a cluster at 50 kiloparsecs radius with 50 kilometers per second velocity will orbit through the halo, periodically crossing the disk. During disk crossings, the black hole can lens background stars if the alignment is right. OGLE 2011b LG0462 at 5,150 light-years from the Sun could be such an ejected cluster black hole on a crossing trajectory, though distinguishing this from other origins requires additional information about its orbit. The number of ejected cluster black holes in the Milky Way is uncertain. Each of the galaxy's 150 globular clusters might have ejected 100 to 1,000 black holes over cosmic time, giving 15,000 to 150,000 ejected cluster black holes wandering the halo. Most orbit at large radii, where microlensing surveys don't monitor enough background stars to catch their lensing events, but a fraction crosses the disk regularly, contributing to the population of detectable wandering black holes. Intermediate mass black holes, those with masses 100 to 100,000 solar masses, might also form in dense clusters through runaway mergers. If a cluster core becomes dense enough, black holes merge repeatedly, building up a single massive black hole at the center. Simulations by Mark Freitag at Stockholm University suggest this runaway process could create 1,000 solar mass black holes in the densest clusters. Observational evidence for such objects is tentative, but includes a few candidates like the source in the cluster G, one orbiting the Andromeda Galaxy, where velocity measurements suggest a central mass of about 20,000 solar masses. These intermediate mass black holes, if they exist and get ejected, would create extraordinarily long microlensing events. With Einstein radii 100 times larger than stellar mass black holes, their lensing events would last decades rather than months. No such events have been definitively detected, suggesting either intermediate mass black holes are rare, or they're located in regions where monitoring is insufficient. Future surveys with continuous coverage over decades might reveal them. The missing galaxies that should surround every black hole. When astronomers announced the discovery of OGLE 2011b LG0462, a stellar mass black hole with no surrounding galaxy, some asked, why would we expect galaxies around black holes? The question reveals a common confusion between stellar mass black holes formed from dying stars and supermassive black holes that reside in galaxy centers. Understanding this distinction clarifies why finding an isolated stellar mass black hole is unusual but not impossible, while finding an isolated supermassive black hole would be shocking. Supermassive black holes, those with masses from 1 million to 10 billion solar masses, sit at the centers of nearly every large galaxy. The Milky Way hosts Sagittarius A star, a 4 million solar mass black hole discovered through observations of stars orbiting the galactic center at velocities up to 5,000 kilometers per second. Reinhard Genzel and Andrea Ghez shared the 2020 Nobel Prize in Physics for this discovery, which required tracking individual stars' motions for decades using adaptive optics on the Keck and VLT telescopes. The connection between galaxies and supermassive black holes is so tight that the black hole mass correlates with galaxy properties. The M-sigma relation, discovered by Laura Ferrarez and David Merritt in 2000, shows that black hole mass equals roughly 1/1000th of the mass of the galaxy's central bulge. More precisely, the black hole mass scales with the bulge velocity, dispersion, the random velocities of stars in the bulge raised to the 4th or 5th power. A galaxy with twice the bulge velocity dispersion has about 16 to 32 times the black hole mass. This correlation implies galaxies and their central black holes form together, or at least evolve in lockstep. The leading theory involves feedback. As the black hole accretes gas and grows, it releases energy through jets and radiation that heats surrounding gas, preventing further star formation in the bulge, and regulating both black hole and galaxy growth. When the black hole reaches the mass predicted by the M-sigma relation, feedback becomes strong enough to expel remaining gas, shutting down both black hole accretion and star formation simultaneously. Because of this connection, supermassive black holes are always in galaxies, or more precisely, galaxies always have central supermassive black holes. Finding a supermassive black hole wandering alone would require ejecting it from its galaxy, which is extraordinarily difficult. The escape velocity from a galaxy center is typically 300 to 1,000 kilometers per second. A supermassive black hole merger can produce recoil velocities up to 5,000 kilometers per second in extreme cases, potentially ejecting the merger remnant. But such extreme mergers are rare, and most supermassive black holes remain bound to their galaxies. A few candidates for recoiling supermassive black holes exist. In 2017, the Hubble Space Telescope imaged 3C186, a quasar 8 billion light-years away, showing it offset by 35,000 light-years from its host galaxy's center and moving at 2,000 kilometers per second. The interpretation: this is a 1 billion solar mass black hole kicked by a recent merger, now escaping its galaxy. The black hole is still accreting gas violently, powering a luminous quasar, but it's unbound and will eventually wander into galactic space alone, a supermassive black hole with no galaxy. But stellar mass black holes are different. They don't form with galaxies. They form inside individual massive stars when those stars exhaust nuclear fuel and collapse. A 2.5 solar mass star doesn't need a galaxy to form. It just needs a giant molecular cloud with enough gas to collapse under self-gravity. While most star formation happens in galaxies where molecular clouds are abundant, isolated star formation can occur in tidal tails from galaxy interactions, in stripped gas from ram pressure encounters, or in primordial gas clouds in the early universe. Moreover, stellar mass black holes can be ejected from their formation sites much more easily than supermassive ones. The escape velocity from the Milky Way's disk at the solar neighborhood is about 550 kilometers per second. Supernova kicks can reach 1,000 kilometers per second, fast enough to eject a stellar mass black hole from the galaxy entirely. Binary merger kicks can reach 5,000 kilometers per second, and even without kicks, black holes in disrupted binaries or ejected from clusters simply drift through the galaxy, unattached to any particular location. The notion that stellar mass black holes should be surrounded by galaxies makes sense only if you think all black holes are like supermassive ones. But stellar mass black holes are fundamentally different. They're stellar corpses, remnants of individual dead stars, with no intrinsic connection to galaxies except that they formed inside them. Once formed, they can wander away, and many do. The Milky Way likely contains 100 million stellar mass black holes scattered throughout the disk and halo, most completely isolated, wandering alone through space. The surprise about OGLE 2011b LG0462 isn't that it's a black hole without a galaxy, it's that we detected it at all. Isolated black holes are invisible unless they accrete gas and emit X-rays, which requires being near a gas source, or unless they lens background stars, which requires chance alignment with our line of sight to monitored stars. The fact that we found one suggests many more exist undetected. Current estimates suggest one stellar mass black hole passes within the Earth-Sun distance of Earth every 100 million years, though at those distances and without accretion, they remain completely invisible. The question for supermassive black holes is different. Could a primordial supermassive black hole exist without a galaxy, formed in the early universe through direct collapse of gas rather than stellar processes? Some theories suggest massive black holes 100,000 to 1 million solar masses could form in dense gas clouds at redshift 10 to 20, about 100 to 500 million years after the Big Bang, through collapse without an intermediate stellar phase. These black holes would serve as seeds for later supermassive black holes. If such primordial black holes exist, some might have remained isolated, never captured by galaxies. They would be wandering intergalactic space now, 13 billion years later, accreting gas at extremely low rates and essentially invisible. The only way to detect them would be through gravitational lensing of background objects. The Einstein radius for a 1 million solar mass black hole at cosmological distances is about 1 arc second, large enough to detect with current surveys. but no convincing candidates have been found, suggesting either primordial supermassive black holes are rare, or our surveys haven't been sensitive enough yet. For OGLE E2011b LG0462, the 7 solar mass firmly places it in the stellar mass category, ruling out any primordial origin or connection to galaxy formation. This is a stellar corpse. A massive star died, collapsed, and left behind this black hole, which then wandered away from wherever it formed. The absence of a galaxy around it is expected, not surprising. What's surprising is that we found it, that the alignment was perfect enough for it to lens a background star, and that astronomers were monitoring that star when it happened. OGLE 2011b LG0462 is a lucky accident, a glimpse at the invisible population of wandering black holes that fill the galaxy in numbers we can only estimate. The 100 million stellar black holes hiding in the Milky Way. The Milky Way has produced stars for 13 billion years. Over that time, hundreds of billions of stars have formed, lived, and died. The most massive stars, those above 20 to 25 solar masses, have lifetimes of only 3 to 10 million years before exhausting their nuclear fuel and collapsing. Some leave neutron stars, others leave black holes. The fraction that form black holes depends on the details of stellar evolution and supernova physics, but estimates suggest about 10 to 30% of massive stars leave black hole remnants, with the rest forming neutron stars or disrupting completely in pair instability supernovae. From stellar population synthesis models that track how stars form, evolve, and die over cosmic time, astronomers estimate the Milky Way should contain about 100 million stellar mass black holes. This number comes from integrating the star formation rate over the galaxy's history, applying the initial mass function that describes how many stars form at each mass, evolving those stars to determine which ones form black holes, and summing the total. Different models give different numbers. Some say 50 million, others say 200 million, but 100 million is a reasonable middle estimate. Yet as of 2024, astronomers have confidently identified only about 60 stellar mass black holes in the Milky Way. Most are in X-ray binaries, where accretion from a companion star makes them visible. A few were discovered through gravitational microlensing, like OGLE 2011b LG0462. A handful were found through radial velocity measurements of stars orbiting invisible companions. The discrepancy is enormous. We found 0.00006% of the black holes that should exist. Where are the missing 99.99994%? The answer: they're dark. Black holes emit no light of their own. They become visible only through interaction with surrounding matter, accreting gas from a companion star, lensing background light, or warping space-time enough to affect nearby objects' motions. Most black holes do none of these things. They drift alone through space at velocities of 50 to 200 kilometers per second, passing through the tenuous interstellar medium without accreting enough to glow, rarely aligning with background stars to create detectable lensing events, and located far from any stars whose motions we could measure. The X-ray binary black holes we know are biased towards certain properties. They're in binaries only about 15% of all black holes based on stellar evolution models. Their companion stars are close enough within a few solar radii that the black hole's gravity can pull gas from the companion. That gas forms an accretion disk, spiraling inward and heating to millions of degrees, emitting X-rays detectable across thousands of light years. Observatories like Chandra, XMM Newton, and RXT have found these systems throughout the galaxy. Cygnus X1, the first black hole candidate discovered in 1964 through X-ray observations by rocket-borne instruments, exemplifies the X-ray binary class. The system contains a 2-1 solar mass black hole accreting from a 4-1 solar mass blue supergiant star in a 5.6-day orbit. The accretion disk glows with X-ray luminosity about 30,000 times the Sun's total luminosity, making it one of the brightest X-ray sources in the sky. But systems like Cygnus X1 are extraordinarily rare, perhaps 1 per million black holes. Most black holes don't have close companions. They're either isolated because they formed from single stars, about 30% of massive stars based on binary surveys, or isolated because supernova kicks disrupted their binaries, ejecting the black hole and companion in opposite directions. Binary disruption efficiency depends on kick velocity and orbital separation, but models suggest 50 to 70% of binaries are disrupted by asymmetric supernovae, leaving both components single. Isolated black holes can accrete from the interstellar medium through Bondi-Hoyle accretion. When a black hole moves through gas at velocity v, it accretes gas from within a capture radius roughly equal to 2 times Newton's gravitational constant times the black hole's mass divided by the velocity squared. For a 1-0 solar mass black hole moving at 50 kilometers per second through gas with density 1 atom per cubic centimeter, typical for the warm interstellar medium, the accretion rate is about 10 to the negative 14th power solar masses per year, or about 1 Earth mass per million years. This accretion rate produces negligible luminosity. The energy released by accretion equals the accretion rate times c squared times an efficiency factor around 10% for black holes. Plugging in the numbers gives luminosity around 10 to the 27th power ergs per second, or about 1 millionth the Sun's luminosity. Even at 1,000 light-years distance, this luminosity would be utterly undetectable with current instruments. The black hole remains effectively invisible despite accreting continuously. Gravitational microlensing offers another detection method, but it's limited by statistics. The probability that a given background star is being lensed by a foreground black hole at any moment is roughly the number of black holes times the Einstein radius squared divided by the area of the sky. With 100 million black holes in the galaxy and Einstein radii of order 1 milliarc second, the instantaneous lensing probability is about 10 to the negative 6th power. That means, out of 1 million monitored stars, about 1 is being lensed at any time. OGLE monitors about 200 million stars in the galactic bulge, so about 200 should be lensed at any moment. Over a year, as lensing events begin and end, the survey detects about 2,000 events. Most are caused by ordinary stars, not black holes. Only about 1 to 2% of events, 20 to 40 per year, are caused by black holes based on event duration and magnification. Over 30 years of surveying, that's 600 to 1,000, 200 black hole lensing events total, a tiny fraction of the 100 million black holes that exist. Radial velocity surveys can detect black holes in wide binaries. If a star has a black hole companion in an orbit of months to years, the star wobbles as it orbits the common center of mass. Precise spectroscopy measures this wobble through Doppler shifts of the star's spectral lines, revealing the companion's mass. The Gaia mission, launched in 2013 to measure positions and velocities of 1 billion stars, has discovered several black holes this way by detecting stars with suspicious wobbles. Gaia BH1, announced in 2022, is a 1-0 solar mass black hole orbiting a Sun-like star every 185 days at a distance of about 1,560 light-years from Earth. The system was identified because Gaia detected the star's wobble, a velocity amplitude of 4 kilometers per second, consistent with an unseen companion. Follow-up spectroscopy confirmed the companion's minimum mass exceeded 5 solar masses, ruling out neutron stars and white dwarfs. The black hole is quiescent, not accreting, and would be invisible without the star's wobble revealing its presence. Gaia BH2, and BH3, announced in 2023 and 2024, brought the Gaia black hole count to 3. BH2 has 8.9 solar masses and orbits a red giant star every 1,277 days at 3,800 light-years distance. BH3 has 32.7 solar masses, the most massive stellar black hole found in the Milky Way, so far orbiting a metal-poor giant star every 11.6 years at 2,000 light-years distance. All three were found through Gaia's astrometric measurements detecting stellar wobbles, a method that's only beginning to tap the black hole population. Gaia's sensitivity peaks for black holes in binaries with orbital periods between 1 month and 10 years. And companion stars bright enough for precise astrometry, roughly 10,000 systems in the galaxy. If Gaia ultimately finds 100 to 1,000 black holes this way, it will still represent less than 0.001% of the total population. The vast majority, those without detectable companions, not lensing monitored stars, and too far from any bright stars to affect their motions, remain invisible and will remain so for the foreseeable future. The missing 100 million black holes aren't missing, they're just dark. They exist throughout the galactic disk and halo, drifting through space on orbits shaped by their formation kicks and subsequent gravitational interactions. They're remnants of stars that died millions to billions of years ago, now invisible monuments to stellar death scattered throughout the galaxy like silent sentinels, detectable only when chance alignments bring them briefly into observability through lensing or rare binary companions. The accretion disk that should glow but doesn't. When matter falls toward a black hole, it doesn't fall straight in. Conservation of angular momentum, the rotational equivalent of linear momentum, prevents direct infall. Instead, the infalling matter settles into an accretion disk, a rotating structure where material spirals inward gradually while shedding angular momentum through viscosity and magnetic fields. As the matter spirals inward, gravitational energy converts to heat, raising the disk's temperature. Close to the black hole, where orbital velocities approach the speed of light, temperatures reach millions or even billions of degrees, causing the disk to glow brilliantly across the electromagnetic spectrum. For a 1-0 solar mass black hole accreting at 1 - billionth of a solar mass per year, a modest accretion rate typical of X-ray binaries in quiescence, the luminosity equals roughly 10% of the accretion rate, times c squared, giving about 10 to the 37th power ergs per second, or 30,000 times the sun's luminosity. This light emerges predominantly as X-rays because the innermost disk regions reach temperatures of 10 million Kelvin or higher, with peak emission in the kilo-electron-volt energy range. Such systems are easily detectable across the galaxy with X-ray telescopes like Chandra or XMM Newton. But accretion requires matter supply. In X-ray binaries, the companion star provides matter through two mechanisms. First, stellar wind particles continuously blown off the star's surface falls into the black hole's gravitational well. Second, if the star expands enough to fill its Roche lobe, the teardrop-shaped region, where the star's gravity dominates over the black hole's matter streams from the star through the L1 Lagrange point toward the black hole. This Roche lobe overflow produces high accretion rates, powering the brightest X-ray binaries. V404 Cygni exemplifies a high accretion rate system. This 9 solar mass black hole orbits a low-mass star every 6.5 days. When the system is in outburst, which happens every few decades, when instabilities in the accretion disk trigger runaway heating, the accretion rate skyrockets to 10 to the -6th power solar masses per year, about 100 million times higher than typical quiescent rates. The disk heats to 100 million Kelvin, emitting X-ray luminosity rivaling 100 million suns. The 2015 outburst was visible to amateur X-ray telescopes, the brightest black hole transient in 25 years. Isolated black holes have no companion stars. Their only matter source is the interstellar medium, the diffuse gas-filling space between stars. This gas has densities of about 0.1 to 1 atoms per cubic centimeter in the warm interstellar medium, where most of the galactic disk's volume resides, or 10 to 100 atoms per cubic centimeter in denser molecular clouds. These densities are trillions of times lower than the atmospheres of stars in binary systems, producing correspondingly lower accretion rates. The Bondi-Hoyle accretion formula describes how an object moving through gas accretes matter. The accretion rate equals pi times the gas density times the Bondi radius squared times the relative velocity, where the Bondi radius equals 2 times Newton's gravitational constant times the object mass, divided by the sum of the sound speed squared and the relative velocity squared. For a 1-0 solar mass black hole moving at 50 km per second through warm ionized gas with density 0.3 atoms per cubic centimeter and sound speed 10 km per second, the accretion rate is about 10 to the negative 14th power solar masses per year. This accretion rate produces luminosity around 10 to the 27th power ergs per second, about 1 millionth the sun's luminosity and 1/10 billionth the luminosity of V404 Cygni in outburst. At 1,000 light-years distance, fairly close by galactic standards, this luminosity corresponds to an apparent magnitude around 30 inches X-rays, far below the detection threshold of any current X-ray telescope. Chandra, the most sensitive X-ray observatory, reaches limiting magnitudes around 20 inches deep exposures, but that's 10 million times brighter than our isolated black hole's emission. Could denser gas increase accretion enough to make isolated black holes visible? If a black hole passed through a molecular cloud with density 1,000 atoms per cubic centimeter, the accretion rate would increase by a factor of 3,000, bringing luminosity to about 10 to the 30th power ergs per second, or 1,000th the sun's luminosity. Still invisible at kiloparsec distances. Only if the black hole passed through the densest cores of molecular clouds with densities above 10 to the 6th power atoms per cubic centimeter would accretion luminosity become marginally detectable, but such encounters are rare and brief. Molecular cloud cores are tiny, typically 0.1 to 1 light-years across, and occupy a minute fraction of the galaxy's volume. A black hole moving at 50 km per second crosses a 1 light-year core in 20,000 years. If the galaxy contains 10,000 such cores and 100 million black holes, the probability that any given black hole is currently crossing a dense core is about 1 in 100,000. That means only about 1,000 black holes at any moment are accreting at rates high enough to potentially detect, and most of those are still too faint or too distant to observe. Another possibility, a black hole might accrete a planet or asteroid. If a rogue planet or asteroid passed within the black hole's tidal radius where tidal forces exceed the object's self-gravity, the object would be torn apart, forming an accretion disk. The disruption luminosity depends on the object's mass and how quickly it's disrupted. A Jupiter-mass planet disrupted over months would produce luminosity comparable to a bright X-ray binary for that duration, potentially detectable if relatively nearby. But planetary captures are even rarer than molecular cloud encounters. The capture cross-section equals roughly the Bondi radius, about 1 astronomical unit for a 1-0 solar mass black hole moving at 50 km per second. The number density of rogue planets in the galaxy is estimated at about 0.01 to 0.1 per cubic light-year, based on microlensing surveys. The rate at which a black hole encounters rogue planets is roughly the cross-section times the density times the velocity, giving about 1 encounter per 10 billion years. Over the Milky Way's lifetime, Each black hole has encountered 0 or 1 rogue planet, producing brief detectable emission if we happen to be observing at the right time and distance. Supernova remnants offer another potential environment. When a massive star explodes, it ejects several solar masses of material at 10,000 to 20,000 kilometers per second. If a nearby black hole sits in the path of this ejector, perhaps another stellar remnant from the same star cluster, it will accrete rapidly as the dense supernova ejector sweeps over it. The accretion rate could reach 10 to the -6th power solar masses per year for years to decades, producing bright X-ray emission comparable to X-ray binaries. There's some evidence for this scenario. In 2020, astronomers reported X-ray observations of the supernova remnant 1E0102, 2 to 7,219 inches, the Small Magellanic Cloud, revealing an X-ray point source offset from the remnant center. The source's X-ray spectrum and luminosity were consistent with a black hole accreting from supernova ejector. If confirmed, this would be a rare example of an isolated black hole made temporarily visible by chance interaction with a supernova. But such events are transient, lasting decades to centuries, and finding them requires monitoring many remnants continuously. For OGLE 2011BLG0462, the absence of X-ray emission from Chandra observations sets limits on accretion rate. The upper limit corresponds to accretion below 10 to the -11th power solar masses per year, consistent with Bondi-Hoyle accretion from the warm interstellar medium, and ruling out high-rate accretion from a molecular cloud or captured object. The black hole is quiescent, accreting only trace amounts of gas as it drifts through space. It doesn't glow. It's invisible, except for the gravitational lens it created during its chance alignment with a background star. This is the typical state for isolated black holes: dark, wandering, undetectable. The other rogue black holes discovered through microlensing, OGLE 2011BLG0462, isn't the only isolated black hole discovered through gravitational microlensing. It's merely the best characterized, with the longest Hubble Space Telescope follow-up campaign and the most precise mass measurement. Several other candidates exist with similar properties: long-duration lensing events, high magnification, absence of detectable lens light, and masses in the black hole range. Each discovery adds to the growing census of wandering black holes and tests our understanding of black hole formation and dynamics. MOA2011B LG191 is the same event as OGLE 2011B LG0462. Both names refer to identical observations by the MOA and OGLE surveys. The dual designation reflects independent detection by separate teams, each using their own naming convention based on survey, year, bulge field number, and event number. When two surveys detect the same event, the naming can be confusing, but it provides valuable confirmation that the detection is real and not an artifact of one survey's analysis pipeline. Another candidate appeared in 2018, OGLE 2011BLG0462, a different event with a similar designation pattern. Wait, that's confusing. Let me clarify. The year in the designation is when the event occurred, not when it was announced. Many events take years to analyze due to the need for multi-epoch Hubble observations and complex modeling. Events discovered in the 2010 seconds might not be published until the 2020 second. The black hole literature contains several candidates from OGLE and MOA data that remain unpublished or published only in conference proceedings. A particularly interesting case is OB 110462, a shorthand designation for OGLE 2011B LG0462 used in some papers. This event's analysis, published by Kailash Sahu in 2022, represents the culmination of a decade-long effort involving 8 epochs of Hubble imaging between 2011 and 2017, ground-based photometry from multiple telescopes, and sophisticated modeling using relativistic microlensing codes. The result, a 7.1 solar mass black hole at 5,150 light years with well-constrained uncertainties. Compared to other microlensing black hole candidates, OB110462 stands out for having astrometric measurements. Most microlensing events are detected photometrically, monitoring brightness changes without high-resolution imaging to measure centroid shifts. Astrometry requires Hubble-class resolution and multiple epochs spanning the event, which is expensive in terms of telescope time and only feasible for a small subset of events. But astrometry breaks degeneracies in the lens parameters, allowing much more precise mass, distance, and velocity determinations. One early candidate for an isolated black hole was MACHO96BLG5, detected in 1996 by the MACO survey monitoring the Large Magellanic Cloud. The event lasted 971 days, the longest microlensing event detected at that time, and reached peak magnification of about 80. Initial analysis suggested a lens mass around 6 solar masses, consistent with a black hole. However, subsequent analysis, including parallax effects from Earth's orbital motion around the Sun, revised the mass upward to about 0.5 solar masses, more consistent with a red dwarf star or white dwarf. The lesson: long duration alone doesn't guarantee a black hole lens. Parallax provides additional constraints. As Earth orbits the Sun, our viewing angle to the lensing event changes slightly, causing small deviations from the symmetric light curve expected for a stationary observer. These deviations depend on the lens distance and velocity. By measuring parallax, astronomers can determine whether the lens is relatively nearby, within a few kiloparsecs, or distant, beyond 10 kiloparsecs, helping distinguish disk lenses from bulge lenses and constraining the mass-distance degeneracy. For OB110462, parallax measurements from combined ground-based and Hubble observations showed the lens is at 5,150 light-years in the disk, not the bulge. This placement is unusual. Most microlensing events have lenses in the disk lensing bulge sources, with median lens distances around 3 to 4 kiloparsecs. A lens at 5,150 light-years is farther than average, closer to the bulge itself. This could indicate the black hole is on an eccentric orbit carrying it through the outer disk, or it could be a bulge black hole on a rare trajectory that brings it close enough to the disk to be detected. Gaia BH1, BH2 and BH3 mentioned earlier aren't microlensing discoveries, they're astrometric discoveries from Gaia's survey of stellar positions and motions. But they complement microlensing discoveries by sampling a different part of parameter space. Black holes in wide binaries with orbital periods months to decades, rather than isolated black holes or tight binaries. Together, microlensing and astrometric surveys are building a multifaceted picture of the black hole population. Gaia BH1's 10 solar mass black hole at 1,560 light-years is the closest known black hole to Earth as of 2024. It orbits a Sun-like star every 185 days in a nearly circular orbit with semi-major axis 1.4 astronomical units between the orbits of Earth and Mars, if scaled to the solar system. The black hole is not accreting despite being relatively close to its companion, likely because the companion hasn't expanded to fill its Roche lobe, and stellar wind accretion is insufficient. The system will eventually become an X-ray binary when the companion evolves into a red giant and begins mass transfer. Gaia BH3's 32.7 solar mass black hole is remarkable for being the most massive stellar black hole in the Milky Way detected so far. It's also orbiting a metal-poor star one with iron abundance, only 3% of the Sun, suggesting the system formed early in the galaxy's history when metal content was low. Low metallicity stars have weaker stellar winds, allowing them to retain more mass and potentially form more massive black holes. The 32.7 solar mass measurement pushes against theoretical limits for stellar black hole formation through direct collapse, raising questions about formation mechanisms. Comparison between microlensing black holes like OB110462 and astrometric black holes like Gaia BH, one shows different selection effects. Microlensing finds isolated black holes or black holes in wide enough binaries that the companion doesn't affect the lensing. It's sensitive to black holes at distances of a few kiloparsecs, the typical distance to bulge stars. Astrometry finds black holes in binaries with bright companions, and it's most sensitive to nearby black holes within 2 kiloparsecs where stellar wobbles are largest. Together, they sample the black hole population from different angles. The total number of black holes discovered through microlensing remains small, perhaps 5 to 10 high-confidence candidates, as of 2024, depending on how strict the criteria are. Most lensing events caused by compact objects have ambiguous masses in the 2 to 5 solar mass range, where the distinction between heavy neutron stars and light black holes is unclear. Only events with masses clearly above 3 solar masses, the upper limit for any plausible neutron star equation of state, are unambiguous black hole detections. Future microlensing surveys will discover hundreds more. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct a microlensing survey monitoring stars in the galactic bulge with sensitivity 1,000 times better than ground-based surveys. Roman will detect about 100,000 microlensing events over its 5-year mission, including an estimated 200 to 500 events caused by stellar mass black holes. The high cadence and infrared sensitivity will allow detailed characterization of event parameters, providing a large sample for statistical studies of the black hole population. The Vera Rubin Observatory, beginning operations in 2025, will contribute through its legacy survey of space and time, monitoring the entire southern sky every few nights. While not optimized for microlensing, Rubin will detect thousands of events, including long-duration ones caused by black holes. Combined with Roman's dedicated microlensing survey, the late 2020 seconds and 2030 seconds will see an explosion in black hole discoveries, transforming our understanding from a handful of examples to a statistically robust population. The astrometric microlensing that revealed position shifts. Gravitational lensing magnifies light, but it does something subtler and equally important. It shifts apparent positions. When a massive object passes in front of a background star, it creates not one, but 2 images of that star, one on each side of the lens. These images are typically separated by milliarc seconds, far too small to resolve even with Hubble, but we can measure their combined effect. The centroid, or brightness, weighted average position of the 2 images shifts slightly compared to the unlensed star's position. The magnitude of this centroid shift depends on the lens mass and geometry. For a lens passing with impact parameter, the minimum angular separation between lens and source equal to the Einstein radius, the centroid shift reaches maximum at roughly 1/3 of the Einstein radius. For OGLE 2011BLG0462, with an Einstein radius of about 5 milliarc seconds, based on the lensing duration and estimated distances, the maximum centroid shift should be about 1.7 milliarc seconds. The actual measured shift was 2.82 milliarc seconds, somewhat larger than this simple estimate, indicating the geometry was particularly favorable. Measuring milliarc-second scale position shifts requires extraordinary precision. Ground-based telescopes, limited by atmospheric turbulence, typically achieve astrometric precision of 10 to 100 milliarc-seconds, even with adaptive optics. The Hubble Space Telescope, orbiting above the atmosphere and achieving diffraction-limited imaging, can measure positions to about 0.1 milliarc-seconds in ideal conditions, using techniques like multiple exposures and point spread function fitting. Kailash Sahu and colleagues used Hubble's Wide Field Camera 3 to image the OGLE E2011b LG0462 field 8 times between 2011 and 2017. The first 4 observations in 2011 and 2012 captured the lensing event itself. The background star was brightened and its position was shifted. The later observations in 2016 and 2017 came after the lensing event ended, showing the star back at its unlensed position and brightness. By comparing positions before, during, and after lensing, the team measured the centroid shift with precision about 0.15 milliarc-seconds. The analysis process is complex. Each Hubble image contains thousands of stars in the field, and measuring positions requires building a reference frame using these stars. The reference frame must account for geometric distortions in the camera, variations in the point spread function across the field, and proper motions of stars between epochs. The team used specialized software to register images to sub-pixel precision, fit point spread functions to each star, and measure centroid positions. One challenge: the lensing source is faint about 23rd magnitude in the infrared and sits in a crowded field where nearby stars can bias position measurements. The team used a technique called difference imaging, subtracting a reference image taken when the lensing event wasn't active from images taken during the event. This removes light from nearby stars, isolating the variable source whose position is being measured. Even so, systematic errors from imperfect subtraction can introduce biases, requiring careful error analysis. The centroid shift measurement directly constrains the angular Einstein radius, the angle subtended by the Einstein radius projected on the sky. For OGLE 2011 BLG0462, this angle is 5.1 milliarc-seconds, with uncertainty about 0.5 milliarc-seconds. The angular Einstein radius depends on lens mass m, lens distance d lens, and source distance d source through the formula. Theta e equals the square root of the quantity 4 times Newton's gravitational constant times m, divided by c squared, times the quantity of d source minus d lens, divided by d source times d lens. In spoken form, the angular Einstein radius equals the square root of 4 times the gravitational constant times the lens mass, divided by the speed of light squared, multiplied by the ratio of the difference in distances divided by the product of distances. When you know theta e from the centroid shift and estimate the distances from stellar populations and galactic models, you can solve for the lens mass m. The distance estimates introduce uncertainty. The source star's distance is estimated at 27,000 light-years, based on its position in the bulge and its intrinsic brightness, inferred from color magnitude diagrams of bulge stars. The lens distance of 5,150 light-years comes from combining the angular Einstein radius with the Einstein radius crossing time, the duration of the lensing event divided by a geometric factor, and the relative proper motion between lens and source. These distance estimates have uncertainties around 10 to 20%, propagating into the mass estimate. The beauty of astrometric microlensing is that it breaks degeneracies present in photometric-only microlensing. With photometry alone, you measure the event duration and magnification, which constrain the combination of mass, distance, and velocity, but don't uniquely determine each parameter. Many different combinations of mass and distance can produce the same duration if velocities adjust appropriately. But astrometry adds the centroid shift, which depends on mass and distance differently than duration does, breaking the degeneracy. Andrew Gould at Ohio State University pioneered astrometric microlensing analysis in the 2000s, showing that Hubble observations could measure centroid shifts for high magnification events and extract unique lens properties. His early predictions suggested that 1 in 10 microlensing events detected by ground-based surveys would be suitable for Hubble follow-up, and that such follow-up would measure black hole masses to 20 to 30% precision. The OGLE 201, 1b, LG04, 62 results validated these predictions. The timeline of observations spanned 6 years. The event was detected in June 2011, when the source star began brightening. Ground-based observations tracked the brightening through peak magnification in August 2011, and the subsequent decline through mid-2012. Hubble observations in July and October 2011 captured the event near peak, measuring both the magnified brightness and the shifted position. Follow-up Hubble observations in March 2012, June 2016, and February 2017 tracked the source as it returned to its unlensed state. The 270-day duration from first detection to return to baseline brightness made this a long event by microlensing standards. Typical events last 10 to 30 days. Events lasting longer than 100 days comprise about 5% of all detections and are prime candidates for compact object lenses. The long duration indicated either a massive lens, a slow relative velocity, or both. Combined with a large centroid shift, the event was recognized early as likely caused by a black hole, motivating the extensive Hubble campaign. Comparing OGLE 2011b LG0462 centroid shift to predictions for various lens masses shows the power of astrometry. A 1 solar mass lens would produce a shift around 0.7 milliarc seconds. A 3 solar mass lens would give 1.2 milliarc seconds. A 7 solar mass lens gives 2 milliarc seconds, close to the observed 2.82 milliarc seconds. A 1.5 solar mass lens would give 3.1 milliarc seconds. The measurement clearly excludes low mass lenses, like red dwarfs or white dwarfs, and clearly favors black hole masses. Future astrometric microlensing will benefit from improved technology. The Nancy Grace Roman Space Telescope will have astrometric precision comparable to Hubble but with 100 times the field of view, allowing it to monitor many microlensing events simultaneously. Roman's dedicated microlensing survey will observe the galactic bulge continuously for 5 years, catching thousands of events and performing astrometric follow-up on hundreds of long-duration candidates. This will build a large sample of black hole masses measured through astrometric microlensing. The Gaia mission, while not focused on microlensing, can contribute through detecting astrometric shifts in bright sources undergoing lensing. Gaia measures positions of stars brighter than 20th magnitude, with precision around 0.1 milliarc second. If a bright star undergoes microlensing by a nearby black hole, Gaia might detect the centroid shift even without detecting the brightening. This serendipitous detection mode could find dozens of events over Gaia's mission lifetime, complementing dedicated microlensing surveys, the neutron star alternative that doesn't fit the data. When the first measurement suggested OGLE 2011b LG0462's lens mass was around 7 solar masses, the immediate question was, could this be a neutron star instead of a black hole? Neutron stars are compact remnants from supernova explosions, supported by neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being squeezed into the same quantum state. They're extraordinarily dense, with masses around 1.4 solar masses compressed into spheres roughly 20 kilometers in diameter, giving densities comparable to atomic nuclei at 10 to the 14th power grams per cubic centimeter. The maximum possible mass for a neutron star depends on the equation of state for nuclear matter at supranuclear densities, densities exceeding those in atomic nuclei. At these extreme densities, we don't know precisely how matter behaves. Laboratory experiments and colliders like RHIC and the LHC probe nuclear matter at temperatures billions of degrees and densities comparable to neutron star cores, but the conditions aren't identical. Theoretical models based on quantum chromodynamics make predictions, but uncertainties remain. The Tolman-Oppenheimer-Volkoff limit, or TOV limit, sets a theoretical maximum neutron star mass based on general relativity and assumptions about the equation of state. J. Robert Oppenheimer and George Volkoff calculated in 1939 that neutron stars couldn't exceed about 0.7 solar masses using the equation of state known at the time. Later refinements with better nuclear physics increased this limit. Modern calculations using realistic equations of state give TOV limits between 2 and 2.5 solar masses, depending on assumptions about nuclear interactions at high density. Observations constrain the maximum neutron star mass empirically. The most massive precisely measured neutron star is PSR J740 plus 6,620, a millisecond pulsar discovered in 2019. Timing measurements and Shapiro delay. The gravitational time delay of pulsar signals passing near the companion star determined the pulsar's mass as 2.08 solar masses with uncertainty about 0.07 solar masses. This is close to the theoretical TOV limit, suggesting we're approaching the maximum possible neutron star mass. Another massive neutron star is PSR J348 plus 0432, a pulsar orbiting a white dwarf with an orbital period of 2.46 hours. The neutron star's mass is 2.01 solar masses, measured through relativistic orbital dynamics. The pulsar emits gravitational waves that slowly shrink the orbit-orbital decay detectable through timing, matching general relativity's predictions and confirming the mass measurement. Both PSR J740 plus 6,620 and PSR J348 plus 0432 sit just below the theoretical maximum. A mass gap exists between the heaviest neutron stars and the lightest black holes. Neutron stars observed in binaries peak around 1.4 solar masses, with a tail extending to 2.1 solar masses. Black holes observed in X-ray binaries start around 5 solar masses and extend to 20 solar masses or more. Between 2.5 and 5 solar masses, very few objects have been detected. This gap might be real, representing a forbidden range where compact remnants can't exist, or it might be an observational selection effect where objects in this range are rare or hard to detect. The origin of the mass gap is debated. One possibility: stars massive enough to leave remnants above 2.5 solar masses undergo exotic collapse processes, fall back of envelope material onto the neutron star, quark-nova transitions, or rapid accretion that push the remnant over the neutron star maximum and into black hole territory. Another possibility: pair, instability supernovae, which occur in stars with initial masses 140 to 260 solar masses, completely disrupt the star and leave no remnant, creating a gap in remnant masses. But this doesn't explain the gap between 2.5 and 5 solar masses for lower mass progenitors. Recent observations have found compact objects in the mass gap, complicating the picture. The LIGO, Virgo Gravitational Wave Event GW190814, detected in August 2019, involved a 2-3 solar mass black hole merging with a 2.6 solar mass compact object. The smaller object's mass falls squarely in the gap. It could be the most massive neutron star ever detected, exceeding theoretical limits and requiring exotic physics, or it could be the lightest black hole, implying the mass gap doesn't exist or is narrower than thought. For OGLE 2011BLG0462, the measured mass of 7.1 solar masses is well above any plausible neutron star maximum. Even if we adopt the most generous equations of state that push the TOV limit to 2, 5 or even 3 solar masses values that require exotic matter like hyperons or quark matter in neutron star cores, 7 solar masses is nearly 3 times the maximum. There's no theoretical framework that allows neutron stars to reach 7 solar masses. The object must be a black hole. Could the mass measurement be wrong? The uncertainty range is 6 to 8.4 solar masses at 95% confidence. Even the lower bound of 6 solar masses is well above neutron star limits. For the measurement to be consistent with a neutron star, the true mass would need to be below 2.5 solar masses, which would require systematic errors more than 2.5 solar masses in magnitude far larger than plausible uncertainties in the analysis. The microlensing formulas relating mass to observables are well tested, and the Hubble astrometric measurements are precise. Another argument against a neutron star, the absence of X-ray emission. Young neutron stars are hot, with surface temperatures around 1 million Kelvin declining over millions of years as the star cools through neutrino emission and photon radiation. A 10 million year old neutron star, a plausible age for OGLE 2011BLG0462 based on typical massive star lifetimes, would have surface temperature around 100,000 Kelvin, emitting thermal X-rays with luminosity about 10 to the 31st power ergs per second, or 100 times the Sun's luminosity. At 5,150 light-years distance, such a neutron star would have X-ray flux detectable by Chandra in a moderate exposure. The fact that Chandra observations found no X-ray source at the lens position rules out typical neutron stars, unless they've cooled far below expectations. Rapid cooling scenarios involving exotic matter, like kaon condensates or quark cores, can cool neutron stars below detectability in 10 million years, but these require fine-tuned nuclear physics and aren't the standard expectation. Pulsations provide another test. Many neutron stars emit beams of radio waves from their magnetic poles, appearing as pulsars if the beams sweep across Earth. The beam covers only a fraction of the sky, so only about 10% of neutron stars are visible as pulsars from any given viewing angle. But radio surveys are sensitive and have discovered over 3,000 pulsars in the Milky Way. If OGLE 2011BLG0462 were a pulsar, it would likely have been detected in radio surveys of the galactic disk. Searches for radio pulsations at the lens position using the Green Bank telescope found nothing. This doesn't rule out a neutron star. It could be a non-pulsing neutron star or a pulsar whose beam doesn't point toward Earth, but it eliminates the most easily detected category of neutron stars. Combined with the mass measurement, the absence of X-rays, and the absence of radio pulsations, the neutron star hypothesis is excluded beyond reasonable doubt. The object is a black hole. The broader lesson, microlensing, can distinguish black holes from neutron stars through precise mass measurements. For masses above 3 solar masses, the distinction is clear. For masses in the 2.5 to 3 solar mass range in the mass gap, additional observations like X-ray or radio searches become critical. For masses below 2.5 solar masses, neutron stars and black holes can't be distinguished from microlensing alone, requiring other diagnostics. OGLE 2011 BLG0462, with its 7 solar mass measurement, leaves no ambiguity. This is a black hole, the velocity that tells the ejection story. The 45 km per second velocity of OGLE 2011 BLG0462 is measured relative to the average motion of stars in that region of the galactic disk. This peculiar velocity, the deviation from circular rotation around the galactic center, encodes information about the black hole's history. Where did it come from? How was it ejected? How long has it been wandering? The velocity provides clues to answer these questions, though not definitive answers without additional trajectory information. To understand what 45 km per second means, we need context about galactic velocities. Stars in the Milky Way's disk orbit the galactic center in roughly circular paths at velocities determined by the enclosed mass. At the Sun's distance, about 27,000 light-years from the galactic center, the circular velocity is approximately 220 km per second. Stars closer to the center orbit faster. Stars farther out orbit slower, following a rotation curve that stays roughly flat from 10,000 to 50,000 light-years radius. Individual stars deviate from perfect circular motion due to perturbations from spiral arms, molecular clouds, and random encounters with other stars. These random velocities, called velocity dispersions, average about 30 km per second for stars in the thin disk where the Sun resides. Young stars have lower dispersions, around 10 to 20 km per second, because they haven't been perturbed much. Old stars have higher dispersions, around 40 to 50 km per second, after billions of years of gravitational kicks. OGLE 2011 BLG0462's 45 km per second. Peculiar velocity is higher than typical thin disk stars, but not extraordinarily high. It's comparable to old disk stars and modest compared to halo stars, which have velocity dispersions around 100 to 150 km per second. This intermediate velocity suggests the black hole received some kick during formation, but not an extreme one. It's consistent with a modest supernova kick, a low-energy binary disruption, or ejection from a globular cluster with moderate escape velocity. The escape velocity from the Milky Way varies with distance from the galactic center. At the solar neighborhood, escape velocity is about 550 km per second. Closer to the galactic center, where the enclosed mass is higher, escape velocity reaches 700 to 800 km per second. At the outer edges of the disk, 50,000 light-years from the center, escape velocity drops to about 300 km per second. OGLE 2011 BL G0462's 45 km per second is well below escape velocity at any radius, meaning the black hole is gravitationally bound to the Milky Way. But bound doesn't mean confined to the disk. A black hole with 45 km per second peculiar velocity can have a vertical component motion perpendicular to the galactic plane that carries it high into the halo. If 30 km per second of the total velocity is vertical, the black hole will rise about 2,000 light-years above the plane before gravity pulls it back down. It would oscillate up and down through the disk with a period of about 100 million years, spending most of its time in the halo, but periodically crossing the disk where it could lens background stars. Reconstructing the black hole's trajectory requires knowing its full three-dimensional velocity vector. Microlensing gives us the transverse velocity motion perpendicular to our line of sight, which is 45 km per second. But the radial velocity motion toward or away from us remains unknown because lensing doesn't measure Doppler shifts. The black hole could be moving toward us at 100 km per second, away from us at 50 kilometers per second, or have zero radial velocity. Each scenario implies a different trajectory and origin. If we assume the black hole's radial velocity is typical for disk stars, somewhere between -30 and +30 kilometers per second, we can estimate its total velocity as between 55 and 75 kilometers per second. Over 10 million years, a plausible age for a black hole formed from a 2.5 solar mass star. This corresponds to traveling 1,600 to 2,300 light-years from its birthplace. Any stellar association or open cluster where it formed has likely dispersed in that time, consistent with the absence of any cluster at the black hole's current location. Comparing to observed pulsar velocities provides context. Pulsars, neutron stars that receive kicks during supernovae, have a measured velocity distribution that peaks around 400 kilometers per second, with a long tail extending to 1,000 kilometers per second or more. About 10% of pulsars have velocities below 100 kilometers per second, and about 2% have velocities below 50 kilometers per second. OGLE 2011 BLG 0462's 45 kilometers per second places it in the lowest 2% of the pulsar distribution, suggesting a particularly symmetric supernova or a failed supernova with minimal kick. The velocity also constrains formation mechanisms. If the black hole formed through a binary black hole merger that produced gravitational wave recoil, typical kick velocities are 100 to 500 kilometers per second based on LIGO-Virgo merger observations. The measured 45 kilometers per second is too low for a typical merger, unless the mass ratio was close to unity and spins were aligned, minimizing recoil. This makes merger origin less likely than supernova origin. For cluster ejection, typical escape velocities from globular clusters are 20 to 50 kilometers per second. OGLE 2011 BLG 0462's velocity matches this range, making cluster ejection plausible. If the black hole was ejected from a cluster with 30 kilometers per second escape velocity and additional velocity from three-body encounters, the total could reach 45 kilometers per second. The black hole would have left the cluster millions of years ago and been orbiting through the galactic halo since then. One way to distinguish origins is through chemical composition. If the black hole had a companion star, which it doesn't now, that star's metallicity would indicate where the system formed. Globular clusters have low metallicities, typically 10 to 30% of solar iron abundance. Disk stars have solar or slightly supersolar metallicities. A low metallicity companion would suggest cluster origin. Solar metallicity would suggest disk origin. But without a companion, we can't measure metallicity. Another clue comes from the black hole's orbital parameters around the galactic center. If we could measure its orbit requiring knowing position, velocity, and time evolution over years to decades, we could determine whether it's on a circular orbit typical of disk stars, an eccentric orbit suggesting ejection from the inner galaxy, or a highly inclined orbit consistent with halo membership. Current data give us only a snapshot, position, and transverse velocity at one moment. Future astrometric observations with Gaia, or follow-up radial velocity measurements, if it had a companion, could reveal orbital parameters. The 45 kilometers per second also affects future detectability. The black hole will continue moving through the galaxy, potentially lensing other background stars. The probability of lensing depends on how many background stars are available and how long the black hole remains in regions where monitoring occurs. If it's on a disk-crossing orbit, it will pass through the galactic bulge region, monitored by OGLE and MOA, every 100 million years or so, creating opportunities for future lensing detections of this same object. But tracking individual black holes through multiple lensing events is nearly impossible. Each lensing event gives a position at one moment, but connecting events separated by millions of years to the same lens requires extraordinary precision in predicting trajectories. Gravitational perturbations from encounters with molecular clouds, spiral arms, and other stars alter trajectories over millions of years, making long-term predictions uncertain. OGLE 2011 BLG 0462 will likely lens again, but we won't know it's the same object. The velocity measurement also has cosmological implications. If stellar mass black holes typically have peculiar velocities of 45 kilometers per second, they'll remain concentrated in the galactic disk and inner halo, where their formation sites are. But if typical velocities are 500 kilometers per second, many black holes will escape the galaxy entirely, wandering into galactic space. The velocity distribution of black holes determines whether they remain associated with galaxies or diffuse into the cosmic web. OGLE 2011 BLG 0462 suggests at least some black holes have low velocities and remain bound. The primordial black holes that might outnumber stars. In 1971, Stephen Hawking proposed a radical idea. Black holes might have formed in the first second after the Big Bang, not from stellar collapse, but from density fluctuations in the early universe. When the universe was extraordinarily dense and hot, quantum fluctuations created regions slightly denser than average. If these overdense regions were large enough and dense enough, they could collapse directly into black holes without ever forming stars. These primordial black holes would be older than any star, predating even the first generation of stellar formation by hundreds of millions of years. The mass range for primordial black holes is enormous, potentially spanning from asteroid mass 10 to the 15th power grams, or about 1/1,000,000,000 of a solar mass, to stellar mass and beyond. The mass depends on when the black hole formed after the Big Bang. Earlier formation produces lighter black holes, because the horizon mass, the mass contained within a causally connected region, was smaller. Black holes forming at 10 to the -24th power seconds after the Big Bang would have masses around 10 to the 15th power grams. Those forming at 1 second would have masses around 100,000 solar masses. Primordial black holes below about 10 to the 15th power grams would have evaporated by now through Hawking radiation. Hawking showed in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon, losing mass at a rate inversely proportional to the square of their mass. The evaporation timescale for a black hole equals roughly 1 divided by the quantity m divided by 10 to the 15th power grams cubed times 10 billion years. A black hole with mass 10 to the 15th power grams evaporates in 10 billion years. Lighter black holes evaporate faster, heavier ones last longer. For primordial black holes with stellar masses, say 1 to 100 solar masses, the evaporation timescale is 10 to the 67th power years for a solar mass black hole. This is vastly longer than the universe's current age of 13.8 billion years. Stellar mass primordial black holes formed in the early universe would still exist today, wandering through the galaxy, indistinguishable from black holes, formed through stellar collapse, except for their age and potentially their spatial distribution. Could OGLE 2011 BLG 0462 be a primordial black hole rather than a stellar remnant? The mass of 7 solar masses falls within the possible primordial range, but several observations argue against it. First, primordial black holes should have a broad mass distribution reflecting the spectrum of density fluctuations in the early universe. Observations from LIGO, Virgo show that stellar black holes have a characteristic mass scale, around 8 solar masses, with a cutoff around 50 solar masses, inconsistent with primordial predictions. OGLE 2011b LG0462's mass-matching stellar black hole masses suggests stellar origin. Second, primordial black holes should be distributed throughout the dark matter halo, not concentrated in the galactic disk. Dark matter formed early and diffused throughout the galaxy's halo, extending to 300,000 light-years or more. If primordial black holes contribute to dark matter, they should follow dark matter's distribution: spherical halo with declining density away from the galactic center. But OGLE 2011b LG0462 is in the disk at 5,150 light-years from the Sun, typical for stellar remnants formed from disk star population. Third, the velocity is wrong for halo objects. Dark matter halo objects have velocity dispersions around 150 to 200 kilometers per second, much higher than OGLE 2011b LG0462's 45 kilometers per second. If the black hole were part of the halo population, its velocity should be typical for halo objects. The low velocity indicates disk membership, not halo membership, again favoring stellar origin. Despite these arguments, primordial black holes remain an intriguing possibility for explaining dark matter. Observations constrain how much dark matter can be primordial black holes in various mass ranges. The MACO project in the 1990 seconds searched for gravitational microlensing of stars in the Large Magellanic Cloud by dark matter in the Milky Way's halo. They detected some events, but the rate was too low to explain all dark matter through compact objects in the 0.01 to 1 solar mass range. Updated constraints from EROS, OGLE, and other surveys rule out primordial black holes as the dominant dark matter component for masses between 10 to the negative 7th power and 10 solar masses. Too many or too few lensing events are detected compared to what a primordial black hole-dominated halo would produce. But the constraints have loopholes. If primordial black holes are clustered rather than uniformly distributed, or if they have a narrow mass function concentrated at specific masses, they could evade detection while still contributing significantly to dark matter. Recent interest in primordial black holes surged after LIGO's first detection in 2015. The binary black hole mergers LIGO detects have masses in the range where primordial black holes might exist. If primordial black holes are common, some fraction should be in binaries formed through dynamical capture in the early universe. These binaries would merge over billions of years, producing gravitational wave signals indistinguishable from stellar binary mergers. Some researchers argue that the LIGO-Virgo merger rate is consistent with primordial black holes comprising a few percent of dark matter. Tests to distinguish primordial from stellar black holes include mass distributions, spin distributions, and merger rates as a function of redshift. Stellar black holes should have masses reflecting the stellar initial mass function, more low mass than high mass, and spins reflecting the angular momentum of their progenitor stars. Primordial black holes should have broader mass distributions and lower spins because they formed from nearly symmetric collapse without rotation. Future gravitational wave observations with better sensitivity will test these predictions. Another test involves gravitational lensing of the cosmic microwave background. Primordial black holes formed before recombination 380,000 years after the Big Bang would lens CMB photons. As those photons travel toward us, the lensing would create small distortions in the CMB temperature and polarization maps. Planck satellite observations constrain primordial black holes in certain mass ranges through the absence of excess lensing, but significant parameter space remains allowed. Asteroid mass primordial black holes, those with masses around 10 to the 17th power 210, to the 20th powergrams, are particularly interesting because they could explain dark matter while evading most observational constraints. They're too light to produce detectable microlensing of stars, but heavy enough to avoid Hawking evaporation. They could contribute to dark matter without being detected by current surveys. Searches for gamma-ray emission from evaporating primordial black holes constrain this scenario, but don't rule it out. If primordial black holes exist in large numbers, wandering black holes like OGLE 2011 BLG 0462 might occasionally be primordial rather than stellar. The only way to distinguish them would be through age indicators, stellar companions, with ages matching the black hole's formation, or associations with stellar populations indicating when formation occurred. Isolated black holes lack these indicators, leaving origin ambiguous. OGLE 2011b LG 0462 is most likely stellar based on its mass, location, and velocity, but a primordial origin can't be entirely excluded. The broader question, whether primordial black holes contribute significantly to dark matter, remains open. They're an attractive candidate because they're made of normal matter that underwent gravitational collapse, avoiding the need for exotic new particles. But observational constraints are tight, limiting them to at most a few % of dark matter in most mass ranges. Future surveys with improved sensitivity to rare lensing events, better gravitational wave detectors, and refined CMB observations will further constrain or detect primordial black holes, potentially revealing a population of ancient black holes older than any star. The future telescopes that will find thousands more. The detection of OGLE 2011 BLG 0462 required years of ground-based monitoring, multiple Hubble Space Telescope observations, and sophisticated analysis. This intensive effort revealed a single black hole, but next-generation facilities will transform wandering black hole astronomy from studying individual cases to statistical populations. Upcoming telescopes will discover hundreds to thousands of isolated black holes through microlensing, astrometry, and other techniques, providing the large samples needed to understand black hole formation, dynamics, and demographics. The Nancy Grace Roman Space Telescope, formerly known as WFIRST, is NASA's next flagship astrophysics mission, scheduled for launch in May 2027. Roman carries a 2.4-meter mirror, the same aperture as Hubble, but with a field of view 100 times larger, allowing it to survey enormous sky areas efficiently. One of Roman's primary science goals is a microlensing survey of the galactic bulge to search for exoplanets, but the same survey will detect stellar mass black holes as a valuable byproduct. Roman's microlensing survey will monitor about 200 million stars in the galactic bulge continuously for at least 5 72-day observing seasons spread over 5 years. The wide field of view, 0.28 square degrees, covers a significant fraction of the bulge in each pointing. The infrared sensitivity at wavelengths 0.932 microns penetrates the dust-obscuring optical observations, detecting fainter stars and improving sensitivity to distant lensing events. The survey will detect an estimated 50,000 to 100,000 microlensing events total over 5 years, based on simulations by Matthew Penny at Louisiana State University and others. Of these, roughly 200 to 500 will be caused by stellar mass black holes, identified by their long durations, high masses derived from detailed modeling, and in many cases, detectable astrometric shifts. Roman's precision astrometry, capable of measuring positions to a few milliarcseconds, will allow mass measurements for many events similar to the Hubble analysis of OGLE 2011 BLG 0462. Unlike Hubble, which requires competitive proposals for each target and can observe only a handful of lensing events per year, Roman will observe thousands simultaneously through its wide field and continuous monitoring. This efficiency makes Roman transformative for black hole detection. Instead of one precisely characterized isolated black hole, we'll have hundreds with well-measured masses, distances, and velocities, enabling statistical studies of the black hole mass function, velocity distribution, and spatial distribution. Roman will also detect intermediate mass black holes if they exist. A 1,000 solar mass black hole lensing a bulge star would produce an event lasting several years with enormous magnification and an astrometric shift of 20 to 50 milliarc seconds easily detectable. The 5-year survey duration is long enough to capture much of such an event. If intermediate mass black holes comprise even 0.01% of compact objects, Roman should detect a few, either confirming their existence or setting stringent upper limits. The Virus C Rubin Observatory, formerly the Large Synoptic Survey Telescope, is a ground-based facility in Chile scheduled to begin science operations in 2025. Rubin has an 8.4-meter primary mirror and a 3.2 gigapixel camera with a field of view of 9.6 square degrees, the largest field of view of any telescope of its size. The Legacy Survey of Space and Time will image the entire visible southern sky every few nights for 10 years, generating 20 terabytes of data nightly. While Rubin isn't optimized for microlensing, its cadence is lower than dedicated surveys, and it observes multiple sky regions. Rather than staring at the galactic bulge, it will detect thousands of microlensing events through sheer volume. With 18,000 square degrees surveyed and millions of stars monitored, long-duration events caused by black holes will appear in the dataset. Rubin's multi-band imaging in 6 filters, from ultraviolet to near-infrared, will provide color information, helping to distinguish different types of lenses. Rubin's contribution will be particularly valuable for detecting high-velocity black holes. A black hole moving at 500 kilometers per second creates shorter lensing events than one moving at 50 kilometers per second. OGLE and MOA, with nightly cadence, can miss these fast events. Rubin's 3-day cadence is better suited to detecting week-to-month duration events, complementing Roman's detection of longer events. Together, Roman and Rubin will sample the black hole velocity distribution across a wide range. The Square Kilometre Array, or SKA, is a radio telescope under construction with components in South Africa and Australia. When completed in the late 2022, SKA will have collecting area approaching 1 square kilometre, distributed across thousands of antennas spanning thousands of kilometers. While primarily designed for 21-centimeter observations of neutral hydrogen, SKA will also conduct pulsar surveys with unprecedented sensitivity. These pulsar surveys will find thousands of new pulsars, including some in binaries with black hole companions. The black holes in such systems are wandering objects that happen to capture or retain companions, providing information about the isolated black hole population. Pulsar timing measurements can determine black hole masses to 1% precision through orbital dynamics, surpassing gravitational wave and microlensing precision. SKA might discover 10 to 100 pulsar black hole binaries, a dramatic increase from the 0 confirmed examples as of 2024. The Extremely Large Telescope, or ELT, is a 39-meter optical infrared telescope under construction in Chile by the European Southern Observatory, scheduled for first light in 2028. ELT's enormous light-gathering power and adaptive optics system, providing near-diffraction limited imaging, will enable direct detection of accretion signatures from isolated black holes. If a black hole passes through a molecular cloud and accretes at rates above 10 to the -12th power solar masses per year, the accretion disk emission might be detectable as a faint infrared source. ELT surveys of dense molecular clouds could discover accreting black holes that would otherwise remain invisible. The accretion is transient, lasting years to decades as the black hole traverses the cloud, so continuous monitoring is needed. ELT's spectroscopic capabilities could measure radial velocities if emission lines are detected, providing the third velocity component missing from microlensing detections and allowing full 3D trajectory reconstruction. Gravitational wave detectors will contribute indirectly. LIGO, Virgo, and CAGRA continue operating with improving sensitivity, detecting binary black hole mergers at increasing distances. The third-generation detectors Einstein Telescope in Europe and Cosmic Explorer in the United States, planned for the 2030 seconds, will be 10 times more sensitive than current detectors, detecting mergers throughout the observable universe and measuring masses, spins, and merger rates with high precision. These measurements constrain the black hole mass function and formation channels, providing context for microlensing discoveries. If gravitational wave observations show that stellar black holes typically have masses 8 to 30 solar masses, then microlensing detections of 7 solar mass black holes like OGLE 2011BLG0462 represent the low-mass tail. If merger products from gravitational wave-detected binaries have typical kick velocities of 200 km per second, then microlensing detections of 45 km per second objects indicate modest kicks. The combination of gravitational waves and microlensing paints a complete picture. By the 2030 seconds, the isolated black hole population will be well characterized statistically. Roman will provide hundreds of precisely measured masses, distances, and velocities. Rubin will add thousands of detections, sampling different velocity and mass ranges. SKA will discover pulsar black hole binaries giving dynamical masses. ELT might find accreting black holes in molecular clouds. Gravitational wave detectors will measure the merger product population. Together, these facilities will answer: how many isolated black holes exist? What's their mass distribution? What's their velocity distribution? Where did they come from? The wandering black holes will transform from mysterious individuals to a well-understood population, the intermediate mass black holes that shouldn't exist. Between stellar mass black holes topping out around 100 solar masses and supermassive black holes starting around 100,000 solar masses lies a mysterious gap. Intermediate mass black holes with masses 100 to 100,000 solar masses. Theory struggles to explain how such black holes form. Stellar collapse produces remnants up to perhaps 50 to 100 solar masses before pair instability supernovae disrupt more massive stars. Supermassive black holes likely grow from smaller seeds through accretion and mergers, but the nature of those seeds remains uncertain. Intermediate mass black holes could be the missing link, or they might not exist at all. The first strong candidate for an intermediate mass black hole appeared in 2009. Astronomers using the Swift and Chandra X-ray observatories detected a source designated HLX 1-inch, the galaxy ESO 243-49, located 290 million light-years from Earth. The source showed dramatic X-ray outbursts, reaching luminosities of 10 to the 42nd power ergs per second, about 10 million times the Sun's luminosity. This luminosity exceeds the Eddington limit for stellar mass black holes, implying a mass above 500 solar masses and possibly as high as 100,000 solar masses. The Eddington limit is the maximum luminosity a black hole can sustain through accretion without blowing away the accreting material through radiation pressure. It equals roughly 30,000 solar luminosities times the black hole mass in solar masses. For HLX, one's luminosity of 10 million solar luminosities, the black hole mass must exceed 300 solar masses. Detailed modeling of the X-ray spectrum and variability suggests a mass around 20,000 solar masses, firmly in the intermediate mass range. HLX-1's location is unusual. It's not at the galaxy's center, but offset by about 3,000 light-years in the outskirts. This suggests it might be the stripped core of a dwarf galaxy that merged with ESO 243-49, with the dwarf's central black hole surviving the merger. Alternatively, it could be an intermediate mass black hole formed through runaway stellar collisions in a dense star cluster that later migrated to its current position through dynamical friction. Another candidate emerged in 2012, 3XMM J215022 4-055108, detected in X-rays by the XMM Newton Observatory. This source sits in a galaxy 800 million light-years away, exhibiting quasi-periodic oscillations in its X-ray emission with a period around 1 hour. The oscillation period correlates with black hole mass in known systems. Stellar mass black holes have periods of milliseconds to seconds, while supermassive black holes have periods of hours to days. The 1 hour period implies a mass around 400 to 10,000 solar masses. Globular clusters offer another hunting ground for intermediate mass black holes. Dense stellar environments like globular clusters could form intermediate mass black holes through runaway mergers. A massive star sinks to the cluster center through dynamical friction, collides with another star, forming a more massive merger product, which sinks further and collides again, repeating until a very massive star or black hole forms. This runaway process requires specific conditions, sufficiently high stellar density, and low escape velocity that might exist in young massive clusters. Omega Centauri, the most massive globular cluster in the Milky Way, with about 10 million solar masses in stars, is a prime candidate for hosting an intermediate mass black hole. Velocity measurements of stars near the center show elevated velocities consistent with a central dark mass of 40,000 solar masses. However, alternative explanations exist. Perhaps a concentration of stellar mass black holes or a disk of dark stellar remnants could produce the same velocity signature without requiring an intermediate mass black hole. NGC 6388 and NGC 6441, two massive globular clusters, also show kinematic evidence for central concentrations of mass. Hubble's Space Telescope observations tracked individual star motions near the centers, finding velocity dispersions higher than expected from the visible stellar mass alone. The excess mass is estimated at 2,000 to 10,000 solar masses, consistent with intermediate mass black holes. But again, alternatives like populations of stellar mass black holes can't be ruled out. Gravitational wave detections provide additional evidence. The event GW190521, detected by LIGO and Virgo in May 2019, involved the merger of black holes with masses 85 and 66 solar masses, producing a 142 solar mass remnant. This is the first definitively detected intermediate mass black hole. The progenitor black holes themselves are puzzling, because masses above 65 solar masses aren't expected from stellar collapse pair instability supernovae should disrupt stars in that mass range. Their existence suggests alternative formation channels, possibly through prior mergers building up mass in dense environments. The pair instability supernova gap exists because very massive stars, those with helium cores above 64 solar masses, produce so much energy from oxygen fusion that photons convert to electron-positron pairs, reducing radiation pressure and causing runaway collapse followed by thermonuclear explosion. The explosion completely disrupts the star, leaving no remnant. Stars with initial masses 140 to 260 solar masses should produce pair instability supernovae, but GW190521's progenitors had masses in the forbidden range, challenging this picture. Possible explanations include hierarchical mergers. Black holes formed from lower mass stars merge to produce 8-5 solar mass black holes, which then merge again to produce 1-4-2 solar mass black holes. This requires multiple generations of mergers in dense environments where remerging is likely before the merger products are ejected. Dense globular clusters or nuclear star clusters around galactic centers could provide such environments. Another formation channel involves direct collapse in metal-poor environments. Low metallicity stars have weaker stellar winds and retain more mass, potentially producing more massive black holes. If a 200 solar mass star with very low metallicity collapses directly without a pair instability supernova, it could leave a 100 solar mass black hole. The first generation of stars, population 3 stars, formed from primordial gas, were likely very massive and metal-free, possibly producing intermediate mass black hole seeds. Isolated intermediate mass black holes wandering the galaxy would be extraordinarily difficult to detect. Their gravitational lensing events would last years to decades, requiring continuous monitoring over timescales exceeding most survey durations. Their accretion luminosity from the interstellar medium would be proportionally higher than stellar mass black holes, perhaps 100 times higher for a 1000 solar mass black hole, but still faint at kiloparsec distances. Only if one passed through a dense molecular cloud or disrupted a star would it become transiently visible. Tidal disruption events offer a detection method. If an intermediate mass black hole passes near a star, tidal forces stronger on the near side than the far side can tear the star apart. The disrupted stellar material forms an accretion disk, producing a bright flare lasting months to years. Several tidal disruption candidates have been detected by optical transient surveys, with luminosities and durations suggesting intermediate mass black holes, though most are likely from stellar mass or supermassive black holes at galactic centers. The question remains, how common are intermediate mass black holes? If every globular cluster contains one, that's 150 inches the Milky Way's halo. If they form through runaway mergers in young massive clusters, perhaps thousands exist in the Milky Way from clusters that have since dispersed. If they're rare formation anomalies, perhaps only a few exist galaxy-wide. Current constraints from microlensing, X-ray surveys, and globular cluster kinematics suggest they're uncommon but not absent. Future surveys might reveal them or constrain their abundance to negligible levels. The cosmic wanderers drifting through the dark matter halo, the Milky Way extends far beyond the visible stars and gas of the disk. Surrounding the luminous galaxy is the dark matter halo, a vast spherical distribution of invisible matter detected only through its gravitational influence on stellar motions and galaxy rotation. This halo extends to at least 300,000 light-years from the galactic center, 10 times the radius of the stellar disk, and contains about 10 times more mass than all the visible matter in stars, gas, and dust combined. Stellar mass black holes wander through this halo, alongside dark matter particles, stellar remnants ejected from the disk, and old halo stars formed in the early galaxy. The black hole population in the halo comes from multiple sources. Black holes kicked out of the disk by supernova explosions at velocities exceeding 500 kilometers per second, black holes ejected from globular clusters that orbit through the halo, merger remnants recoiling from binary black hole coalescence, and possibly primordial black holes formed in the first second after the Big Bang. The density of black holes in the halo is far lower than in the disk. In the solar neighborhood, stellar mass black holes have a number density around 0.0001 per cubic light-year, one black hole per 10,000 cubic light-years. In the halo at 100,000 light-years from the galactic center, the density might be 100 to 1,000 times lower, about one black hole per 1 million to 10 million cubic light-years. The total number of halo black holes could be 10 million to 100 million, spread across an enormous volume. These halo black holes orbit the galactic center on elongated elliptical orbits, with periods ranging from 100 million to several billion years. Some have orbits that bring them periodically through the disk, where they could lens background stars during disk passages. Others remain in the halo permanently, never approaching close enough to the disk for microlensing surveys to detect them. Their isolation is extreme. Typical separations between halo black holes are thousands of light-years, and most will never encounter another black hole or star throughout cosmic time. The velocity distribution of halo black holes reflects how they were ejected. Black holes, kicked by supernovae with velocities 500 to 1,000 kilometers per second, have orbits that carry them 50,000 to 100,000 light-years from the disk before gravity turns them around. Their orbits are highly eccentric, long and thin, rather than circular, with apocenters, farthest points, in the outer halo, and pericenters, closest points, passing through or near the disk. The orbital period might be 500 million years, meaning the black hole crosses the disk twice per orbit. During disk crossings, the black hole's probability of lensing a monitored star increases dramatically because the stellar density is much higher in the disk than the halo. If microlensing surveys monitor 200 million bulge stars and a black hole crosses the disk along a line of sight to the bulge, the lensing probability is about 10 to the -6th power per crossing 1 in a million. With 10 million halo black holes making perhaps 20 disk crossings over 10 billion years, the total number of crossings is 200 million, implying about 200 lensing events from halo black holes over cosmic time. But most of those events occurred in the past or will occur in the future when no surveys are operating. In any given decade of monitoring, the expected number of halo black hole lensing events is about 0.021 event every 50 years. OGLE 2011BLG0462, with its 5,150 light-year distance and 45 km per second velocity, is more consistent with a disk black hole than a halo black hole, but some fraction of detected events might be halo members on disk-crossing orbits. The dark matter halo structure influences black hole orbits. The halo isn't uniform, but has a density profile, higher density near the galactic center, declining with distance. The profile is well approximated by the Navarro-Frank-White, or NFW profile, where density falls as 1 over the radius at small radii and 1 over the radius cubed at large radii. Black holes orbiting in this potential experience time-varying gravitational force as they move through regions of different density. This varying force causes orbital precession. The orbit's orientation slowly rotates and can scatter black holes to different orbits through resonances with the halo structure. Over billions of years, black hole orbits evolve from their initial configurations, set at formation to a relaxed distribution shaped by the halo potential. The timescale for this relaxation is roughly the crossing time, the time to traverse the halo times the number of crossings needed to randomize the orbit, approximately 10 billion years for typical halo orbit. Encounters with dark matter subhalos, clumps of dark matter that survived galactic mergers, can also perturb black hole orbits. Simulations of galaxy formation show that halos contain thousands of subhalos with masses ranging from millions to billions of solar masses. When a black hole passes near a subhalo, the gravitational interaction can change the black hole's velocity and orbital energy, potentially ejecting it from the galaxy entirely or sending it into the inner halo. The local group, the collection of galaxies including the Milky Way, Andromeda, and dozens of dwarf galaxies, complicates the picture. Black holes in the outskirts of the Milky Way's halo might be perturbed by Andromeda's gravitational field as the two galaxies approach each other. Andromeda is moving toward the Milky Way at about 110 kilometers per second and will collide in about 4 billion years. Black holes in the outer halos might be stripped during the merger, ending up in intergalactic space between the merging galaxies. The probability that a wandering black hole passes near Earth is low but non-zero. A black hole with typical halo velocity 150 kilometers per second passing within 1 light-year of the Sun, close enough to potentially perturb Oort cloud objects, has a cross-section of about 2 square light-years. The number density of halo black holes at the solar neighborhood is about 0.00001 per cubic light-year. The rate at which black holes pass within 1 light-year is roughly the density times the cross-section times the velocity, giving about 1 passage per 100 million years. Such a passage wouldn't be catastrophic. A 1-0 solar mass black hole passing 1 light-year away exerts gravitational perturbations on Oort cloud comets, comparable to those from passing stars, which happen every few million years. Some comets might be deflected toward the inner solar system, increasing impact rates on Earth slightly for a few million years. But the black hole itself wouldn't directly threaten Earth, even at 1 light-year. Its gravity is negligible compared to the Sun's. Closer passages are much rarer. A black hole passing within 1,000 astronomical units, about 25 times Neptune's orbit, would occur roughly every 10 billion years, comparable to the universe's current age. A passage within 10 astronomical units, closer than Saturn, would occur every 10 to the 16th power years, far longer than the age of the universe. The solar system has likely never been closely approached by a wandering black hole, and likely never will be. Detection of halo black holes passing through the solar neighborhood might be possible with future astrometric surveys. Gaia measures positions and velocities of 1 billion stars with precision around 0.1 milliarcsecond. If a black hole passes within 10 light-years, its gravity would deflect nearby stars' positions by microarcseconds to milliarcseconds, potentially detectable with careful analysis. The deflection pattern multiple stars deflected systematically in a direction pointing toward the black hole would reveal the black hole's presence even without direct lensing. The cosmic wanderers drifting through the dark matter halo represent the most isolated objects in the universe. Unlike stars, which emit light and can be seen across vast distances, or planets, which orbit stars, these black holes are alone, separated from neighbors by thousands of light-years, moving through near emptiness at velocities of hundreds of kilometers per second. They're remnants of stars that died billions of years ago, kicked by supernovae or ejected by gravitational encounters, now orbiting through the halo on trajectories that will continue for trillions of years until the galaxy itself disrupts. OGLE 2011b LG0462 might be one of these wanderers, detected briefly during a disk crossing, or it might be a disk resident that never left its formation region. We can't know without more information about its orbit, but its discovery proves that wandering black holes exist, that they can be detected through gravitational lensing, and that the galaxy contains a hidden population of dark objects drifting through space, invisible monuments to stellar death, silent wanderers in the cosmic dark.